Our universe might be a grand and convincing illusion. What if everything we think is real, from the stars above to the ground beneath your feet, is not what it seems at all? We are about to take a journey through 50 of the most bizarre space theories that directly challenge our understanding of reality. This is not a standard science lesson. It is an exploration of the cosmos' wildest what-if scenarios, ideas that defy conventional logic and stretch the fabric of what we think is possible. By the end, you will have a new perspective on the very nature of existence, questioning the foundation of everything you know. We will confront the possibility that we live in a simulation, that time itself might be an elaborate trick, and that our entire history could be a carefully crafted fiction. So, what is the strangest idea about reality you are willing to entertain? This first theory asks a question so profound it can stop you in your tracks. What if our entire universe, from the vast cosmic web of galaxies down to the smallest particle in your hand, is not a physical place at all, but an incredibly sophisticated digital simulation? This is the core of the simulation hypothesis, an idea that has moved from science fiction into serious philosophical debate. The argument was most famously formalized by the philosopher Nick Bostrom. He presents a compelling trilemma, a three-part logical puzzle. He suggests that at least one of the following statements must be true. First, that almost every civilization at our level of technological development goes extinct before it becomes capable of creating realistic simulations. Second, that even if they survive, advanced civilizations have exactly zero interest in running simulations of their own evolutionary history. Or third, and this is the punchline, we are almost certainly living inside a simulation right now. Bostrom's reasoning is statistical. If even one civilization survives long enough to reach a post-human stage, a stage where computing power is essentially limitless, then it could run countless highly detailed ancestor simulations. The number of simulated minds would vastly outnumber the one original biological civilization. Therefore, if such simulations are possible and likely, the odds are overwhelming that any given conscious experience, including yours as you listen to this, is happening inside one of those simulations, not in base reality. This is not just a thought experiment about futuristic video games. It challenges the bedrock of reality itself. If true, the laws of physics are not fundamental truths of nature, but simply the programmed rules of the simulation, the source code of our universe. The stars are not balls of burning gas, but rendered points of light. Your memories, your feelings, your sense of self could all be lines of complex data. It reframes everything we perceive as real into something that is, at its heart, informational. While we have no definitive proof, some scientists and thinkers point to potential glitches in the matrix, odd quantum behaviors, or unexplained limits in our universe that could be interpreted as signs of a simulated environment running on finite processing power. The idea is so captivating it has shaped countless stories, most famously in films where characters discover the world is a digital construct. But this theory pushes beyond fiction, forcing us to confront a haunting possibility. Our search for meaning in the cosmos might actually be a search for the programmer. The simulation hypothesis forces us to question the very substance of reality, but another theory suggests the problem is not with the substance, but with the space it occupies. Our world feels solid, three-dimensional with depth and volume. Yet a radical idea from the cutting edge of theoretical physics proposes this is all a magnificent illusion. We may be living inside a cosmic hologram. This is not a metaphor. The holographic principle suggests that all the information that makes up our three-dimensional universe, every star, every planet, every person, is actually encoded on a distant, two-dimensional surface that surrounds us. Think of it like a security hologram on a credit card. That shimmering, three-dimensional eagle you see is not really there. It is a projection from flat, two-dimensional patterns etched into the plastic. In the same way, our rich, volumetric reality could be a projection from data stored on the universe's ultimate boundary. This astonishing idea did not come from nowhere. It emerged from one of the most profound puzzles in modern physics, the black hole information paradox. When matter falls into a black hole, it vanishes from our universe, seemingly destroying all information about what that matter was. This violates a core tenet of quantum mechanics, which states that information can never be truly destroyed. In the 1970s, physicist Jacob Bekenstein made a startling calculation. He found that the maximum amount of information or entropy a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon, its two-dimensional boundary. It was as if all the data about everything inside the black hole was painted on its surface. Later, building on string theory, physicists like Leonard Susskind and Gerard T. Hooft proposed this was not just a black hole quirk, but a fundamental property of the universe. The holographic principle states that the information content of any region of space is bound by the area of its surface, not its volume. In essence, our three-dimensional world is a projection from a vast, flat, two-dimensional screen at the edge of everything we can see. This flips our intuition completely. The world we experience, with its depth and solidity, is like a movie screen. The true reality is the flat film reel spinning in the projector. Your sense of touching this table, the feeling of wind on your face, the vast distance to a galaxy, all of it could be a seamless, interactive hologram generated from data we cannot directly perceive. It challenges the most basic assumption of our existence, that we live in three dimensions of space. We may just be watching the show. If our reality is a hologram, a projection from a flat cosmic screen, then what does that say about the observer, the mind that perceives it all? This leads us to one of the most unsettling thought experiments in all of science, a paradox that questions whether any of us are truly here at all. It is called the Boltzmann brain paradox. The idea stems from the second law of thermodynamics, which states that the universe naturally tends toward disorder, a state called entropy. A shattered cup will not reassemble itself, and a hot drink will always cool down. Our universe, however, is a stunning exception to this rule. It is incredibly ordered, filled with complex structures like galaxies, planets, and life. To explain this, physicists like Ludwig Boltzmann suggested that our orderly cosmos might just be a rare, random fluctuation in an otherwise vast and eternal sea of maximum entropy, a chaotic void. In an infinite expanse of time and space, even the most wildly improbable events will eventually happen by pure chance. Our universe, with all its galaxies and history, could be one such colossal but temporary statistical accident. But here is where the paradox truly twists the knife. If a fully formed, ordered universe can pop into existence from random fluctuations, then it is astronomically more likely for a much smaller, simpler ordered structure to form. Specifically, a single, self-aware brain. Imagine a disembodied brain, complete with false memories and a perfectly convincing sensory experience of an entire universe, spontaneously assembling from the quantum chaos of a void. This Boltzmann brain would believe it has a body, a past, and is looking up at real stars. It would be utterly convinced of its own reality, yet it would be alone, floating in nothingness, a momentary glitch in the cosmic noise. The chilling implication is that, statistically, you are far more likely to be such a randomly generated brain having a brief, delusional hallucination of a coherent universe than you are to be a real person in a real, 13.8 billion-year-old cosmos. Your memories of yesterday, your knowledge of science, even your understanding of this very paradox, could be nothing more than phantom data generated by a fluctuation. It makes the simulation hypothesis seem almost cozy by comparison. At least in a simulation, there is a programmer and a reality outside the code. The Boltzmann brain suggests there may be nothing at all outside your own isolated and temporary consciousness. This is not just a philosophical curiosity, it is a serious problem for cosmological models that predict an eternal, inflationary universe. If such a cosmos goes on forever, then Boltzmann brains should outnumber ordinary observers like us by an infinite margin. The fact that we do not see evidence of brains popping into existence around us is a major puzzle, forcing scientists to refine their theories of the universe's origin and ultimate fate. It confronts us with a profound question about trust. Can we even trust our own memories and observations if they are, by the raw numbers, the least likely explanation for our existence? The universe we perceive feels solid and continuous, but this paradox suggests it might be the most fragile and improbable illusion of all. The fragility suggested by a Boltzmann brain is a cosmic loneliness, but what if the universe offers a way out, a door instead of a void? Einstein's theory of general relativity, the very framework that describes black holes, also contains the mathematical seeds for their bizarre opposites and for tunnels through the fabric of reality itself. These are white holes and wormholes. While a black hole's gravity is so intense that nothing, not even light, can escape its event horizon, a white hole is theorized to be its exact temporal reverse. Imagine a cosmic fountain that only pours out. Matter and energy could only emerge from a white hole, never fall in. It is a one-way exit door from the universe, or perhaps an entrance from somewhere else. The equations allow for such an object, but they present a profound puzzle. A white hole would violate the second law of thermodynamics by seemingly creating order from nothing, making most physicists believe they are mathematically possible but physically improbable, a fleeting moment that would instantly collapse. Yet, some speculative theories suggest the Big Bang itself could have been a primordial white hole, the ultimate eruption of matter and space-time from a singularity. If black holes are drains, white holes are the mysterious, unseen sources, but the real magic happens when you connect the two. This is where the wormhole or Einstein-Rosen bridge enters the story. The math shows that the intense gravity of a black hole could, in theory, warp spacetime so severely that it connects to another point in the universe, or even another universe entirely via a white hole. This tunnel through the higher dimensions of spacetime would be a shortcut, a cosmic subway linking places billions of light-years apart. The implications are staggering. Travel through a traversable wormhole would not just be faster than light travel, it would be instantaneous from the traveler's perspective, a genuine leap across the cosmos. And because spacetime is interwoven, crossing such a bridge could also mean leaping through time. Arriving at the other end, you might find yourself in a different era entirely. This is not mere fantasy, it is a direct consequence of solving Einstein's field equations with specific configurations of matter and energy. So why have we never seen one? The problem is stability. The equations suggest that any wormhole natural enough to form would be incredibly unstable, pinching shut in an instant. To hold it open, to make it traversable, would require a form of matter with negative energy density, something that creates a repulsive gravitational effect. We call this exotic matter. While tiny amounts of negative energy might be possible through quantum effects like the Casimir force, the quantities needed to prop open a wormhole large enough for a person are astronomical and purely hypothetical. Furthermore, any attempt to use a wormhole for time travel introduces vicious paradoxes, like going back in time and preventing your own birth. Many physicists believe the laws of quantum mechanics might conspire to prevent such paradoxes, perhaps by making the wormhole collapse the moment a time loop is created. The search for these cosmic shortcuts continues not with telescopes, but within the profound depths of mathematical possibility. They remind us that our universe's rulebook, written in the language of relativity, contains chapters we have only begun to read, passages that describe not just how space bends, but how it might be stitched together. Wormholes stitch together distant points in space, but what if the very fabric of time we navigate has been secretly altered? a theory so audacious it claims nearly 3 centuries of our past are a complete fiction. This is the phantom time hypothesis, a controversial idea proposed by a German historian named Heribert Illig in the 1990s. He argues that the years between 614 and 911 Anno Domini, a span of 297 years, never actually happened. According to this radical revision, we are not living in the 21st century, but somewhere closer to the early 18th century. Our calendar, he claims, is off by almost 300 years. The theory suggests this chronological forgery was a deliberate conspiracy, orchestrated by the Holy Roman Emperor Otto III and Pope Sylvester II around the year 1000. Their alleged motive to place Otto's reign symbolically at the dawn of a new millennium, thereby increasing his prestige and power. To make this work, they would have needed to fabricate historical records, invent fictional rulers, and backdate events on a massive scale. Proponents of the idea point to several puzzling inconsistencies as potential evidence. They note a perceived lack of original archaeological artifacts and distinctive architectural styles from that specific period in Europe, suggesting a gap in material culture. Astronomical records also come under scrutiny. For instance, accounts of solar eclipses from that era, when calculated backwards with modern astronomy, sometimes do not align perfectly with the dates and locations described in medieval chronicles. These anomalies, they argue, are the glitches in a fabricated timeline. Mainstream historians and scientists, however, have issued comprehensive and forceful rebuttals. The archaeological record, while less dense in some regions for the early Middle Ages, is far from empty, with coins, manuscripts, and building foundations that firmly anchor the timeline. The astronomical arguments have largely been debunked by more precise historical analysis and a better understanding of how ancient observers recorded such events, often with symbolic or political intent rather than strict scientific accuracy. Most conclusively, the theory completely collapses when looking outside Europe. Detailed records from the Byzantine Empire, the Islamic Caliphates, China, and Mesoamerica all independently document events and rulers across those exact centuries, creating an interlocking web of history that would be impossible to globally coordinate and fake. The phantom time hypothesis stands as a fascinating case study in historical skepticism, forcing us to examine how we verify the past. While its central claim is almost universally rejected by experts, it serves as a stark reminder that our timeline is a constructed narrative, a story we piece together from fragments. It challenges us to ask what other stories might be woven into the calendar we take for granted. While the phantom time hypothesis questions our historical records, another theory challenges the very laws we use to interpret the cosmos. Mainstream cosmology tells us gravity is the great architect of the universe, sculpting galaxies and guiding planets in a silent, dark vacuum. But a controversial alternative, known as the electric universe theory, proposes we have the story completely backwards. It argues that electricity and plasma, not gravity, are the dominant forces shaping everything we see in space. This is not a minor adjustment, it is a full-scale rebellion against conventional astrophysics. Proponents of this idea view the cosmos not as an empty void dotted with isolated islands of matter, but as a vast, interconnected circuit alive with flowing electric currents. In this model, space is filled with a diffuse sea of charged particles called plasma, often called the fourth state of matter. Because plasma is an excellent conductor of electricity, it can carry currents across immense distances, forming filaments and cells that structure the cosmos on the grandest scales. So, what does this radically different lens reveal? It completely reinterprets the formation and behavior of galaxies. In the standard model, galaxies are held together by the gravity of invisible dark matter. The electric universe theory suggests that the majestic spiral arms of a galaxy are not simply stars orbiting a central point, but are the visible traces of vast, rotating Birkeland currents, cosmic power lines twisting through space. The intense magnetic fields and energetic jets observed at the hearts of galaxies are not powered solely by black holes, but by galactic-scale electrical discharges. This perspective also rewrites the history of our own solar system. Conventional science describes a calm, gradual process where planets coalesced from a dusty disk around the young sun. The electric universe proposes a far more dramatic, electrically charged past. It suggests that planets were not formed in their current orbits, but were ejected or captured in a period of cosmic electrical instability. The surfaces of rocky planets like Mars and our Moon, scarred with vast canyons and crater chains, are interpreted not as the results of random impacts or water erosion alone, but as the scars of stupendous planetary lightning strikes called electric discharge machining. Even familiar cosmic events are seen through this shocking lens. A supernova, typically explained as the gravitational collapse and explosion of a massive star, could instead be viewed as a stellar circuit breaking, a cosmic short circuit that releases a titanic flash of electrical energy. The intricate filamentary structures seen in many nebulas are seen as direct evidence of plasma physics at work, not just expanding gas clouds. To its advocates, this model elegantly explains many celestial phenomena without the need for unseen entities like dark matter or dark energy. They argue that laboratory experiments with plasma can reproduce scaled-down versions of galactic shapes and nebulous structures, suggesting the underlying physics is electromagnetic, not gravitational. Mainstream astrophysicists, however, overwhelmingly reject these claims. They point out that while electromagnetic forces are crucial on small scales, like in solar flares, gravity is demonstrably the dominant force on the scale of planets, stars, and galaxies. The mathematical predictions of gravity have been confirmed with extraordinary precision, from the orbit of Mercury to the detection of gravitational waves. Critics argue that the electric universe theory fails to provide quantitative, testable predictions that match observations as accurately as the Standard Model, and that it ignores the overwhelming evidence for gravity's cosmic role. Whether seen as a revolutionary truth or a profound misconception, the electric universe forces a vital question. Are we interpreting the lights in the sky with the right dictionary, or is the cosmos speaking a language of power and current we have only just begun to hear? Electric forces may rewrite cosmic history, but quantum mechanics confronts us with a deeper, more personal fragmentation. At the subatomic level, particles exist in a haze of probability, a superposition of all possible states until the moment we observe them. The act of looking forces a choice, a single outcome plucked from the quantum fog. But what happens to all those other possibilities, the paths not taken? The many worlds interpretation offers a staggering answer. It proposes they are not lost at all. Every quantum event, every tiny decision a particle makes, does not collapse the possibilities into one. Instead, the universe itself splits. Each possible outcome plays out in its own newly created, fully real branch of reality. This is not a metaphor. In this view, reality is a constantly forking tree, with every twig representing a complete and separate universe. Think of the famous Schrödinger's cat experiment. In the standard interpretation, the cat in the box is both alive and dead until you look, at which point it becomes one or the other. In the many worlds view, when you open the box, the universe divides. In one branch, you find a relieved, purring cat. In another, equally real branch, you find a tragic outcome. Both views are real, both experiences are genuine, but now forever separated along diverging timelines. The implications of this are almost impossible to fully grasp. It means that every conceivable event that could happen does happen somewhere. A version of you decided to wear a blue shirt today, another version chose red. In one universe, you took that different job offer years ago. In another, a historical battle ended with the opposite victor, reshaping the world. Every choice, every random quantum fluctuation spawns new worlds without end. This creates a cosmos of truly infinite variety, where every possible version of Earth and every possible version of you exists in a vast, ever-expanding multiverse. This challenges our deepest notions of identity and free will. If every decision creates a new universe where the alternative choice is also made, then are we truly choosing anything? Or are we simply experiencing one path on an infinite map where all roads are traveled? The you listening to this is just one thread in an unimaginably vast tapestry of selves. Some of those other yous are nearly identical, differing only by the position of a single atom. Others live in worlds where the laws of physics are subtly different or where humanity never evolved. The theory also provides a radical solution to the paradox of quantum observation. There is no mysterious collapse of the wave function because nothing ever collapses. The observer themselves becomes entangled with the system and splits along with it. Each version of the observer sees a single, definite result, completely unaware of the other branches. While this interpretation is elegant to some physicists, avoiding the need for a special role for consciousness, its cost is an almost absurd proliferation of realities. Critics argue it is ontologically extravagant, creating more than is necessary to explain what we see. Yet it persists because it emerges directly from the mathematics of quantum theory without adding extra rules. It forces us to confront the true scale of possibility. Somewhere in the branching infinity, there is a universe where you're reading this script aloud instead of hearing it. Another where this channel does not exist. The weight of infinite selves can feel isolating, or it can feel liberating, a reminder that reality is far stranger and more abundant than our single, linear experience can ever contain. Branching into infinite worlds may seem like the ultimate expansion of reality. But what if our experience of time is not a single flowing river, but a rigid geometric prison? This brings us to one of the most peculiar and personally charged ideas on the fringe of cosmology, the time cube theory. Proposed by the late Jean Rey, this concept is not a peer-reviewed scientific model, but a dense, poetic, and often cryptic personal philosophy. It stands as a stark example of how far outside the box thinking can venture, even when it veers completely off the map of conventional understanding. At its core, the theory rejects the linear, one-day-at-a-time model of time we all live by. Instead, Rey declared that time is cubic. He proposed that 4 distinct 24-hour days are happening simultaneously at any given moment. In his view, a single rotation of Earth does not represent one day, but rather exposes 4 different days to the 4 imaginary corners of a cube. Each corner corresponds to a different phase, a different experience of reality happening at once. He associated these with dawn, noon, dusk, and midnight, but not as sequential points. They were all present, all now. To visualize this, picture a simple cube. Each of its 8 corners could represent a unique intersection of these simultaneous days and other dualities, like life and anti-life. For Rey, humanity was trapped in what he called a single-corner belief, a limited, linear perception that blinded us to the full, cubic truth of existence. He argued that academic and religious institutions perpetuated this false, one-day lie to control the population. His writings and online presentations were a passionate, often frustrated attempt to awaken people to what he called the greatest discovery of all time. Mainstream physics and philosophy have universally rejected the time cube theory. It offers no mathematical framework, makes no testable predictions, and contradicts every observable phenomenon related to time, from the consistent progression of day and night to the precise measurements of atomic clocks. Scientists point out that time, as we understand it from relativity, is a dimension intertwined with space, not a geometric shape with independent, simultaneous segments. Yet, the theory's value lies not in its scientific merit, but as a cultural artifact of extreme cognitive dissent. It represents a raw, unfiltered attempt to break free from perceived intellectual constraints, to declare that the most basic assumption of our daily lives, the march of time itself, is a profound illusion. In that sense, it echoes, in a wildly distorted mirror, the same spirit of questioning that drives more rigorous theories. It asks us to doubt what seems unquestionable, even if the proposed answer seems incomprehensible. The time cube stands as a monument to the outer limits of human speculation, a reminder that the search for truth can sometimes lead to places so strange they have no bridge back to the world we know. It challenges us on a fundamental level not to believe its specific geometry, but to ask ourselves what other invisible, unquestioned structures shape our perception of reality. The branching infinities of many worlds and the rigid geometry of Time Cube both grapple with the nature of existence, but a more grounded crisis is unfolding at the very edge of known physics. It centers on the most destructive objects in the cosmos, and it threatens to tear apart our understanding of reality at its foundation. This is the black hole information paradox. At its heart, this is not just a puzzle about black holes. It is a brutal conflict between the two most successful theories ever devised, general relativity and quantum mechanics. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime by mass and energy. It predicts that when a star collapses beyond a certain point, it forms a black hole, a region of space where gravity is so intense that nothing, not even light, can escape its boundary, the event horizon. Once something crosses that horizon, according to relativity, it is lost forever to the outside universe, crushed into the central singularity. Quantum mechanics, the rulebook for the subatomic world, operates on entirely different principles. One of its most sacred laws is the principle of unitarity, which states that information is never truly destroyed. Information, in this quantum sense, is the complete specification of a system. It is the difference between the ashes of a burned book and the intact pages. The ashes still contain all the atoms of the book, but the information, the specific arrangement of those atoms into words and sentences, seems lost. Quantum mechanics insists that even if you burn the book, the information is not gone. It is just scrambled into an incredibly complex form within the smoke and heat. It is always, in principle, recoverable. This is where the paradox screams into being. When an object falls into a black hole, general relativity says it, and all the information about what it was made of, its shape, its history, is irretrievably lost behind the event horizon, eventually destroyed at the singularity. Quantum mechanics declares this impossible. Information cannot vanish, so who is right? For decades, this was a philosophical stalemate. Then, in the 1970s, Stephen Hawking made a revolutionary discovery. Using quantum theory near the event horizon, he showed that black holes are not perfectly black. They should slowly leak radiation, now called Hawking radiation. This radiation is created from the vacuum of space itself, just outside the event horizon. Pairs of virtual particles constantly pop in and out of existence. Normally, they annihilate each other instantly, but at the black hole's edge, one particle can fall in while its partner escapes, becoming real radiation. This process slowly steals energy or mass from the black hole, causing it to evaporate over astronomical timescales. Hawking's initial calculation suggested this escaping radiation was completely random, pure thermal noise. It carried no information about what had fallen in, so when the black hole finally evaporates completely, all the information about everything it ever consumed would be permanently erased from the universe. This was the paradox made real. To resolve it, physicists have proposed mind-bending solutions. One radical idea is the firewall hypothesis. It suggests that the event horizon is not a smooth, empty space as relativity predicts, but a searing wall of high-energy particles. Anything hitting it would be instantly incinerated. This firewall would prevent information from falling into the black hole in the first place, preserving it at the horizon. but it would violently contradict Einstein's prediction that crossing the horizon should be uneventful. Another leading solution comes from Hawking himself, who later revised his view. He proposed that information is not lost, but is gradually encoded into the Hawking radiation itself, in incredibly subtle correlations between the emitted particles. It would be like burning that book, but if you could collect every single ash particle, every wisp of smoke, and measure their quantum states with impossible precision, you could, in theory, reconstruct every word. The information escapes, but in a form so scrambled it is for all practical purposes lost. The most recent and intriguing idea comes from the holographic principle we discussed earlier. It suggests the information of what falls in is never actually inside the black hole. It remains painted on the event horizon's surface, the two-dimensional boundary. As the black hole evaporates, this information is slowly released back into the universe via the Hawking radiation. The paradox remains the greatest unsolved problem in theoretical physics because it points to a missing piece, a theory of quantum gravity that can reconcile the cosmic scale of relativity with the tiny quantum world. The fate of information is the fate of causality itself. If information can be destroyed, then the past is not fixed, and the logical chain of cause and effect that underpins all of science begins to unravel. The universe would have amnesia, and reality would be built on a foundation that can forget. The fate of information in a black hole is a battle for cosmic memory. But what if the entire universe is moving with a purpose, pulled by a ghost we cannot see? Astronomers have discovered something that should not be happening, a current in the cosmic ocean. They call it the dark flow. For decades, the bedrock of cosmology has been the principle that the universe is isotropic and homogeneous. In simpler terms, it should look roughly the same in every direction, and there should be no preferred center or overall motion on the largest scales. The expansion of the universe, driven by dark energy, is supposed to be smooth and even, like dots on an inflating balloon, all moving apart from each other. But when scientists began to study the motion of enormous clusters of galaxies, they found a startling anomaly. These clusters, each containing hundreds or thousands of galaxies, are not just drifting apart with the expansion. They appear to be streaming collectively at a tremendous speed of over 2 million miles per hour, all in the same specific direction. It is as if a vast, invisible hand is tugging on the fabric of spacetime itself, pulling these titanic structures toward a point on the cosmic horizon. This motion cannot be explained by the gravitational pull of any known structure in our observable universe. The combined mass of every galaxy, every cluster, every filament of the cosmic web we can see is not enough to create this coherent, high-speed flow. The source of the pull must lie beyond the cosmic horizon, beyond the limit of light that has had time to reach us since the Big Bang. This is where the theories become breathtaking. One possibility is that the dark flow is evidence of a colossal structure that predates our own universe. Imagine the fabric of reality as a vast sheet. Our Big Bang might have been a local event, a tear or an eruption on that sheet. The dark flow could be the gravitational influence of an immense mass lying outside our erupted bubble, a piece of the original cosmic landscape tugging on everything inside our newborn universe. Another, even more radical idea is that we are feeling the tug of another universe entirely. In certain multiverse models, like the eternal inflation theory, our universe is one bubble in a frothing, infinite sea of other bubble universes, each with its own laws of physics. These bubbles are not completely isolated. They can gravitationally influence their neighbors through the higher dimensional space in which they both float. The mysterious pull of the dark flow could be the first indirect evidence of such a neighboring cosmos, a universe parallel to our own but forever out of sight, its immense gravity creating a current in our cosmic sea. Critics of the dark flow point to potential systematic errors in the data or alternative explanations within our own cosmos. Yet, the observation persists through multiple studies, a stubborn cosmic whisper that something is out there pulling. It challenges the very notion that our observable universe is all there is to see. We may be like sailors on a ship, feeling a powerful current but unable to see the distant continent that creates it. The dark flow suggests our cosmic home is not adrift in a random void, but is perhaps part of a larger geography, a single room in an infinite mansion whose other doors we have not yet found. The dark flow hints at a cosmos far larger than our own, but what if our entire universe is not a one-time event but part of an endless breathing cycle? This is the theory of the Big Bounce, a cosmic heartbeat that replaces a singular beginning with an eternal rhythm. In the standard Big Bang model, our universe exploded into existence from an infinitely dense, infinitely hot singularity about 13.8 billion years ago, and it has been expanding and cooling ever since. It is a story with a definitive, dramatic start. The Big Bounce offers a different epic. It proposes that our universe is not the first, but merely the latest in an infinite series. In this cyclic model, the universe expands from a hot, dense state, just as we observe, but that expansion eventually slows, halts, and reverses. Driven by gravity, all matter and energy would then come crashing back together in a cataclysmic event cosmologists call the Big Crunch. Everything, galaxies, stars, planets, even the fabric of spacetime itself would collapse into an ultra-dense state. But here is the crucial twist. Instead of ending in a permanent singularity, this collapse rebounds. The universe reaches a maximum density and then springs back outward, triggering a new Big Bang and a new cycle of expansion. Our entire cosmic history, from the first light to the last star, would be just one phase in an endless loop of cosmic death and rebirth. This idea fundamentally challenges the notion of a singular beginning. There is no creation from nothing, no absolute start of time. Time itself, in this model, may extend infinitely into the past and future, with each cycle resetting the cosmic clock. The Big Bang was not the beginning of everything, it was simply a turning point, a moment of renewal. This cyclic vision is deeply appealing. It mirrors natural cycles we see everywhere, from the changing seasons to the beating of a heart. It offers a kind of cosmic immortality, a universe that never truly dies but continually transforms. It also elegantly addresses a profound question left by the standard model. What came before the Big Bang? The Big Bounce provides an answer, another universe, another era of existence that contracted down to give birth to our own. For this to be physically possible, the theory requires a mechanism to allow a collapse to rebound into a new expansion. Some models incorporate concepts from string theory or modifications to Einstein's equations, suggesting that at the highest densities, repulsive quantum forces could become dominant, acting like a cosmic trampoline. Others tie the cycle to the mysterious force of dark energy, which currently drives the universe's accelerated expansion. Perhaps dark energy will eventually fade or reverse, allowing gravity to take over and begin the long contraction. While the Big Bounce is a compelling narrative, it faces significant challenges from current observations. The evidence for cosmic inflation, a period of ultra-rapid expansion in the universe's first fractions of a second, is very strong. This inflationary model predicts specific patterns in the cosmic microwave background radiation, the afterglow of the Big Bang which we have observed. A pure cyclic model without inflation struggles to explain these precise patterns. Furthermore, the second law of thermodynamics presents a haunting problem. Entropy, or disorder, increases with each cycle. If the universe has already gone through an infinite number of cycles, entropy should have reached its maximum state by now, resulting in a cold, uniform void, a fate we clearly have not met. Some theorists propose that each bounce somehow resets entropy, but explaining how remains a major puzzle. The Big Bounce stands as a powerful alternative to a universe with a single, definitive birth. It trades a solitary genesis for an eternal return. asking us to consider whether our cosmos is a unique story or merely the latest chapter in a book with no first page. The cosmic heartbeat of the Big Bounce offers a rhythm of renewal, but it still requires a moment of collapse and rebirth. What if the universe required neither a bang nor a bounce, but simply always was? This was the elegant, now largely abandoned vision of the steady-state theory. For decades, it was the Big Bang's most formidable rival, proposing a universe with no beginning and no end, an eternal, unchanging entity in its large-scale appearance. The core idea, developed by astronomers Fred Hoyle, Thomas Gold, and Hermann Bondi in the late 1940s, was beautifully simple. As the universe expands, galaxies move apart, which should cause the overall density of matter to thin out over time. The steady-state model fixed this by proposing that new matter is continuously created out of nothing, at a rate so slow it is undetectable in a laboratory. Just a few atoms per cubic kilometer every century would be enough. This trickle of new hydrogen would gradually coalesce to form new stars and galaxies, filling in the gaps left by expansion. The result is a cosmos that forever looks the same on average, a perfect, self-renewing equilibrium. There is no need for a dramatic origin story, no hot, dense beginning, just an endless, serene process of renewal. It was a philosophically pleasing idea, a universe that always existed and always would, with no troubling questions about what came before. Its downfall, however, came from a discovery that shook cosmology to its core, the cosmic microwave background radiation. In the mid-1960s, Arno Penzias and Robert Wilson at Bell Labs detected a faint, uniform static coming from every direction in the sky. This was not instrument noise, it was the cooled and stretched afterglow of a hot, dense, fiery beginning, the definitive echo of the Big Bang. The steady-state theory had no convincing explanation for this all-pervasive radiation. It predicted a cold, dark universe, not one filled with the thermal remnant of a primordial fireball. This single observation became the theory's death knell for most scientists, solidifying the Big Bang as the standard model of cosmology, yet the idea never completely vanished. Modified versions, often called quasi-steady-state or plasma cosmology models, persist on the fringes. Some proponents suggest the background radiation could be explained by other means, like the scattered light from ancient stars or processes within a dynamic, eternal plasma. Others incorporate elements of the steady state into more complex cyclical models, attempting to salvage its eternal nature while accounting for the evidence. While these alternatives lack the broad evidence and predictive power of the inflationary Big Bang model, they serve an important purpose. They remind us that our current understanding, however successful, was once a challenger itself. The steady-state theory stands as a monument to a different kind of cosmic vision, one not of explosive birth and eventual decay, but of quiet, endless persistence. It asks us if our preference for a story with a clear beginning is a reflection of the universe's true nature or simply a preference of the human mind. The eternal serenity of the steady-state theory offers no place for cosmic catastrophe, yet a persistent modern myth insists our solar system harbors a hidden agent of doom. This is the legend of Planet X, also known as Nibiru, a supposed rogue world on a colossal, elliptical orbit that will one day sweep through the inner solar system, triggering cataclysmic earthquakes, volcanic eruptions, and pole shifts that will wipe human civilization from the Earth. Unlike the theories grounded in physics, this idea springs from a controversial fusion of ancient astronaut speculation and modern apocalyptic anxiety. Its primary architect was the late author Zecharia Sitchin, who in the 1970s published his interpretations of ancient Sumerian cuneiform tablets. Sitchin, who was not a trained archaeologist or linguist, proposed that these texts told of a race of beings called the Anunnaki who came from a planet called Nibiru. He claimed Nibiru orbits our Sun on a long, comet-like path that brings it into the inner solar system only once every 3,600 years. According to his narrative, the Anunnaki genetically engineered humanity hundreds of thousands of years ago to serve as slave laborers mining gold on Earth. This entire saga, he argued, was recorded in literal detail by the Sumerians. Mainstream scholars universally reject Sitchin's translations, stating he misinterpreted Sumerian mythology, assigning astronomical and extraterrestrial meanings to texts that are clearly poetic, religious, and metaphorical. The word Nibiru in actual Sumerian context refers to a crossing point or a celestial object associated with the god Marduk, often linked to the planet Jupiter or possibly Venus, not a hidden 12th planet. Despite this scholarly dismissal, the idea took on a life of its own. In the late 20th century, it merged with broader doomsday prophecies and the legitimate scientific search for a hypothetical planet X beyond Neptune, a search that actually led to the discovery of Pluto. Conspiracy theorists seized upon this, arguing that NASA and world governments were hiding the truth about Nibiru's imminent return. Predictions for its catastrophic arrival have been repeatedly set and then quietly moved forward from the early 2000s to 2012 to other dates that have since passed without event. From an astronomical standpoint, the Nibiru described by believers cannot exist. An object with such a massive, elliptical orbit passing through the inner solar system would have profound and obvious gravitational effects on the orbits of the known planets, effects that our precise planetary tracking would have detected centuries ago. Its approach would be glaringly visible to every amateur astronomer on the planet for years before its arrival. The persistence of the myth, however, is a powerful phenomenon in itself. It taps into a deep-seated human fascination with cyclical catastrophe and hidden knowledge, a modern echo of flood myths or comet fears. It represents a cultural undercurrent where ancient texts are seen as coded messages and official science is viewed with suspicion. While it offers no scientific challenge to reality, the Nibiru cataclysm theory presents a profound psychological one, revealing how easily narrative can override evidence and how the timeless fear of the sky falling can dress itself in the language of planets and orbits. The fear of a hidden planet reveals our anxiety about unseen cosmic forces, but a far more profound silence haunts our search for intelligent life. It is a question first posed bluntly by physicist Enrico Fermi over lunch in the 1950s, a question now known as the Fermi paradox. The universe is unimaginably vast and ancient, with hundreds of billions of stars in our galaxy alone, many of which host planets. Given the sheer numbers and the time available, intelligent civilizations should have arisen many times over. Some of these civilizations would likely be millions of years more advanced than our own, capable of technologies that would make their presence obvious across the galaxy. They could build colossal structures, send out self-replicating probes, or fill the cosmos with signals. Yet we see nothing, we hear only silence. The sky is empty of visitors and strangely quiet. So, where is everybody? This paradox is not just a puzzle, it is a haunting riddle about our place in the cosmos. Among the many proposed solutions, from the grim possibility that civilizations always destroy themselves to the idea that we are simply the first, one answer stands out for its profound and unsettling implications. It is called the Zoo hypothesis. This idea suggests that advanced extraterrestrial civilizations are not absent. They are here. They are watching us right now, but they are following a strict policy of non-interference, a galactic prime directive. In this scenario, Earth is a protected planet, a wildlife preserve or a cosmic zoo, and humanity is the exhibit. The more advanced species of the galaxy have deliberately quarantined our solar system, shielding us from their presence to allow our civilization to develop naturally, without outside influence or contamination. They observe us from a distance, perhaps with undetectable technology, studying our evolution, our cultures, and our struggles as we would observe animals in a national park, careful not to cross the boundary and alter the natural behavior of the subjects. The ethical reasoning behind such a policy is compelling. A vastly older civilization would likely view our nascent technological society as fragile, both culturally and biologically. Making contact could shatter our belief systems, trigger global panic, or lead to our dependency or exploitation. It could be an act of supreme arrogance, like an adult barging into a kindergarten classroom and trying to govern the children's games. By remaining hidden, they grant us the dignity of our own path, for better or worse. This hypothesis transforms the great silence from a sign of loneliness into a sign of deliberate restraint. The emptiness is not empty at all, it is a one-way mirror. Every unexplained light in the sky, every mysterious radar blip, could be interpreted not as a visit, but as a routine checkup by the cosmic zookeepers. This idea carries a deep existential weight. If true, it means we are not masters of our own destiny in the way we believe. Our greatest achievements, our wars, our art, our exploration of space are all being catalogued by unseen observers. It raises the question of when, or if, we will ever graduate from the zoo. Would contact come only when we reach a certain level of technological maturity or ethical wisdom, perhaps when we stop threatening our own planet with extinction? Or are we destined to remain a living museum piece, a quaint example of a pre-contact species, forever behind the galactic velvet rope? The zoo hypothesis offers no easy comfort. It replaces the fear of being alone with the unease of being watched, and the hope of discovery with the patience of a very, very long wait. The zoo hypothesis offers a universe of quiet observers, but another answer to the great silence paints a cosmos far more sinister and lonely. This is the dark forest theory, a grim solution to the Fermi paradox born from science fiction that has since echoed in the halls of serious scientific discussion. It proposes that the universe is not a zoo, but a dark, endless forest. Every civilization is a hunter, armed and hidden in the trees, terrified of revealing its location. In this forest, the only safe strategy is absolute silence, and the only logical response to detecting another hunter is immediate, overwhelming annihilation. The logic is built on a few chilling assumptions. First, survival is the primary need of any civilization. Second, you can never be certain of another civilization's intentions. Their technology might be far more advanced, their ethics completely alien. They could see you as a resource, a threat, or simply something to be cleared away. The gap between a civilization that can communicate across the stars and one that can launch a planet-killing weapon might be terrifyingly small. Given this inherent uncertainty and the high stakes of extinction, the safest assumption is that any other civilization you detect is a mortal danger. Therefore, the moment you discover another signal, you have a choice. You can announce your own location with a reply, hoping for peaceful contact, or you can strike first, eliminating the potential threat before it can do the same to you. In a dark forest, the rational choice is to shoot. This theory explains the silence perfectly. Every civilization that survives learns the same brutal lesson: hide or die. They cloak their emissions, avoid broadcasting their presence, and scan the heavens not for friends but for threats. A careless signal, like our own radio and television broadcasts leaking into space, is not a greeting, it is a beacon that marks a target. It suggests that the reason we have not heard from anyone is not because they are not there, but because the survivors are the ones who know how to stay utterly quiet. Interstellar diplomacy, in this view, is not a hopeful dream but a fatal fantasy. Communication is not a bridge, it is a trigger. The first and only message between civilizations might be the flash of a relativistic kill vehicle, a projectile accelerated to a fraction of light speed, striking a planet with the force of countless nuclear bombs. There would be no conversation, no negotiation, just one silent hunter eliminating another from a safe, untraceable distance. This transforms our search for extraterrestrial intelligence from a quest for companionship into a potentially catastrophic risk. Listening is safe, but answering, or worse, actively broadcasting, could be an invitation for disaster. The dark forest offers no comfort, only a stark warning. The emptiness of space is not a void waiting to be filled, but a battlefield swept clean by a law of cosmic survival where the only winning move is to never, ever be seen. The dark forest presents a universe of hidden predators, but what if we are not native to this battlefield at all? Our very existence on Earth might be the result of a cosmic delivery or even a deliberate planting. This is the theory of panspermia, the idea that life is not a unique miracle of our planet, but a hardy traveler spreading its seeds across the galaxy. In its simplest form, panspermia suggests that the fundamental building blocks of life, like amino acids and organic compounds, are common throughout space, hitching rides on asteroids, comets, and interstellar dust. When these celestial bodies crash into a young, suitable planet like the early Earth, they deliver the raw ingredients for biology, essentially jump-starting the process that leads to living cells. We have found evidence for this in meteorites recovered on Earth, which contain complex organic molecules, proving that the chemistry of life can indeed survive the harsh journey through space. Some extremophile microorganisms on Earth can endure incredible radiation, vacuum, and temperature extremes, suggesting that if tucked inside a protective rock, life might survive an interstellar voyage lasting millions of years. This theory elegantly solves the puzzle of how life appeared on Earth so quickly after the planet cooled, as if the starter kit arrived just as conditions became tolerable. But there is a more provocative twist, a version that injects purpose into the process. This is directed panspermia, proposed by Nobel laureate Francis Crick and chemist Leslie Orgel. This idea suggests that life on Earth was no accident of celestial mechanics. It was a deliberate act of biological seeding by an advanced extraterrestrial civilization. In this scenario, an ancient race, perhaps facing their own world's demise or simply driven by a desire to propagate life, loaded microbial cargo onto unmanned spacecraft and fired them toward promising star systems. Our planet was chosen as a fertile garden, and we are the harvest of that ancient sowing. The motivations could range from altruistic, a kind of galactic biodiversity project, to practical, like creating future homes or resource outposts for their own eventual expansion. Directed panspermia reframes the origin of life from a random chemical fluke to a planned inheritance. It implies that our deepest genetic code might contain a message or a signature from our cosmic ancestors, a biological made-by tag waiting to be decoded. While compelling, both theories face significant hurdles. For natural panspermia, the greatest challenge is the immense radiation-drenched distances between stars, a gauntlet that even the hardiest microbe might not survive. Directed panspermia, while solving the targeting problem, raises the question of the original origin, simply pushing the mystery of life's beginning to another world and another time. Yet the core idea is profoundly humbling. It suggests we are not the center of a biological story, but a single chapter in a saga written across light years. Our family tree may have roots not in a primordial pond, but in the icy heart of a comet from another star. Whether by chance or design, we might all be immigrants in this universe, carrying within us a lineage that stretches back to the dust between the stars. The silent seeding of life across the cosmos asks how matter becomes mind, but a far more intimate mystery lies within the 3 pounds of tissue inside your own skull. Consciousness, the raw experience of being, of seeing red, feeling joy, or remembering a scent, remains science's greatest unsolved puzzle. This is the hard problem of consciousness, the question of how and why physical processes in the brain give rise to subjective experience at all. Could the answer lie not in biology alone, but in the bizarre, probabilistic world of the very small? Quantum consciousness theory suggests it might, proposing that the seat of awareness is not the brain's wiring, but the strange quantum events happening inside it. The most famous model is the Orchestrated Objective Reduction Theory, or ORCH, developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They argue that classical physics, which governs the brain like a complex computer, cannot explain the non-algorithmic, intuitive leaps of human thought or the unified nature of conscious experience. Instead, they look to the quantum level, specifically to structures inside our neurons called microtubules. These are tiny, cylindrical scaffolds that help maintain the cell's shape and transport materials. In the ORCH model, these microtubules are more than cellular plumbing, they are quantum computers. They're proposed that proteins within these tubes can exist in quantum superposition, holding multiple states simultaneously, and then collapse into a single, definite state in a process called objective reduction. This collapse, according to Penrose, is not random, but influenced by a non-computable aspect of reality, linked to the very geometry of spacetime at the Planck scale. Each collapse event is a moment of proto-consciousness. Billions of these events orchestrated across the brain then give rise to our full, flowing stream of awareness. The implications are staggering. If consciousness is rooted in quantum processes, it could explain phenomena that baffle neuroscience, like the binding problem, how the brain integrates colors, sounds, and smells from different regions into a single, seamless experience. Quantum entanglement, the spooky connection between particles across distance, could provide a mechanism for this instantaneous unity. More profoundly, it challenges a purely materialistic view of the mind. In this framework, consciousness is not an emergent byproduct of neural complexity, but a fundamental feature of the universe, accessed and amplified by the brain's biological quantum system. It opens a door, however controversial, to concepts like free will not being an illusion, but a genuine expression of quantum indeterminacy influencing our decisions. It even allows for speculative ideas about the soul or an afterlife, suggesting that quantum information constituting consciousness might not be destroyed at death, but could perhaps dissipate or persist in some form. The theory, however, stands on fiercely contested ground. Most neuroscientists and physicists are deeply skeptical. Critics argue the warm, wet, noisy environment of the brain is utterly hostile to delicate quantum superpositions, which in laboratories require extreme cold and isolation to maintain for even microseconds. They see the brain as a classic, if complex, electrochemical system, with no need for quantum magic to explain its functions. Furthermore, the specifics of how quantum collapses translate to specific thoughts or feelings remain vague. Yet, the ORCH model persists because it tackles the hard problem head-on, daring to propose a bridge between the objective world of physics and the subjective world of experience. It forces us to consider a radical possibility that to understand the deepest nature of our own minds, we may need to peer into the shimmering, uncertain heart of reality itself. Quantum consciousness suggests our minds might tap into a deeper layer of reality, but what if the glitches are not in our perception but in the world itself? This brings us to a strange and deeply personal phenomenon known as the Mandela effect. It describes a situation where a large group of people collectively misremembers a specific detail or event, often with an unnerving sense of certainty. The name comes from the most famous example. Many people vividly recall news reports that Nelson Mandela died in prison during the 1980s, complete with memories of his widow's speech and public mourning. In reality, Mandela was released in 1990, became president of South Africa, and died in 2013. For those who shared this false memory, the discovery felt like a jolt, a crack in their personal history. This is not about simple forgetfulness. The Mandela effect involves strikingly consistent, detailed false memories shared by thousands, sometimes millions. Another classic example is the beloved children's book series. A vast number of adults would swear on their childhood that it was spelled Berenstain Bears with an E. The actual spelling is Berenstain with an A. people recall the E on the book covers in library catalogs, even in their own memories of sounding it out as children. The intensity of this shared error is what makes it so unsettling. Other examples pepper pop culture. Many remember the evil queen in Snow White saying, "Mirror, mirror on the wall," but the actual Disney line is "Magic mirror on the wall." People insist the Monopoly man wears a monocle. He does not. They recall the fruit of the Loom logo featuring a cornucopia. It never had one. Each instance creates a community of people who feel their past has been subtly rewritten. So what is happening here? Mainstream psychology offers compelling, down-to-earth explanations. Our memories are not perfect recordings, they are reconstructions. We store fragments and our brains fill in the gaps using schemas or mental shortcuts based on common patterns. Berenstein fits a more common surname pattern than the unusual Berenstein, so our brains auto-correct it. Mirror, mirror is a more poetic and familiar phrase from the original fairy tale, so it overwrites the actual movie quote. Once a false memory is formed, it can be reinforced through social contagion, as we discuss it online and validate each other's incorrect recollections, creating a powerful echo chamber. This is a well-documented process called confabulation. Yet, for those who experience the Mandela effect, these psychological explanations can feel inadequate. The emotional resonance is too strong, the shared details too specific. This has given rise to a fringe theory that is pure science fiction, but one that resonates deeply with our earlier discussions of the multiverse. Some propose that the Mandela effect is not a memory error at all, but literal evidence of timeline shifts or reality glitches. In this view, when large groups remember something that never happened here, they are actually remembering a version that did happen in a parallel universe. According to the many worlds interpretation, every quantum decision spawns a new branch of reality. Perhaps the theory goes, our timeline has somehow merged with or crossed over from a nearby branch where Nelson Mandela did die in the 80s, or where the books were indeed spelled with an E. We are not misremembering, we are remembering correctly, but from a reality that is no longer our own. Our collective consciousness retains a faint echo of a world that slipped away. Others suggest a more technological glitch, tying it to the simulation hypothesis. If we live in a vast digital construct, then the Mandela effect could be the result of a software update that changed certain details, leaving residual data in the minds of some users, or a bug that causes two slightly different versions of the simulation to briefly overlap. While there is no scientific evidence for these explanations, they fulfill a deep human desire to make sense of a profoundly disorienting experience. They transform a simple memory error into a sign of something grander, a crack in the monolith of a single, objective reality. The Mandela effect ultimately lies in the unsettling space between a proven psychological phenomenon and a cultural myth. It challenges our trust in both our own minds and the solidity of the world around us. Are these shared false memories merely the brain's elegant, error-prone way of managing information? Or could they be the faint, lingering fingerprints of other lives we might have lived in worlds just out of reach? These collective false memories feel personal, a glitch in our mental software, but what if the glitches are not in our minds but written into the universe's oldest photograph? This brings us to the cosmic microwave background radiation, the faint, cold afterglow of the Big Bang itself. It is the oldest light we can see, a snapshot of the infant universe when it was just 380,000 years old, a nearly perfect thermal blanket stretched across the entire sky. For decades, this cosmic background was hailed as the ultimate confirmation of the Big Bang model, a smooth and isotropic echo of creation. But as our satellites mapped it with ever greater precision, they began to find something unsettling. The universe's baby picture has strange, large-scale blemishes, anomalies that defy our standard explanations. The most famous of these is a feature cosmologists have dramatically nicknamed the axis of evil. It sounds like a villain's plot from a space opera, but it is a very real and very puzzling alignment in the data. When scientists analyze the tiny temperature fluctuations in the cosmic microwave background, the hot and cold spots that seeded all future galaxies, they expect these spots to be randomly distributed. There should be no preferred direction, no cosmic north or south. Yet, the data reveals a surprising alignment. The patterns of hot and cold appear to line up along a specific axis, a single preferred plane running through the universe, as if the cosmos has a subtle tilt or a spin we were not meant to see. This violates a core principle of cosmology, the assumption that the universe is the same in all directions on the largest scales. It is as if you painted a room with a perfectly random splatter pattern, only to step back and see the dots mysteriously lining up along the line of the ceiling. The standard model of inflation, the period of ultra-rapid expansion just after the Big Bang, struggles to explain how such a large-scale directional preference could have formed. Then there is the cold spot, an even more bizarre feature. In a region of the southern sky, there is an area of the microwave background that is significantly colder than the surrounding haze. It is not just a small fluctuation, it is a colossal, circular chill about 1 billion light-years across. At first, astronomers thought it might be a giant void, an enormous bubble of relatively empty space between the galactic filaments. As light travels through such a void, it loses energy, creating a cold spot in the background radiation. But surveys have failed to find a void large enough or empty enough to explain the cold spot's profound temperature drop. It remains an unexplained frigid patch on the cosmic map. So, what could these anomalies mean? Some theorists propose they are not glitches in the data, but cracks in our story, evidence of a cosmos that existed before our own Big Bang. The axis of evil could be the lingering imprint of a prior universe, a kind of cosmic fossil whose structure subtly influenced the birth of our own. Perhaps our universe is not the first cycle in an eternal bounce, but was born from the collapse or collision of a previous cosmic era, inheriting a faint directional memory from its parent. An even more radical explanation involves a direct collision with another universe. In the multiverse framework, where our cosmos is one bubble in an endless froth of inflating space, bubble universes can sometimes collide. The cold spot, in particular, has been proposed as a potential bruise from such an impact. Imagine two soap bubbles gently touching. At the point of contact, energy would be transferred. In cosmic terms, a collision with a neighboring universe bubble could have siphoned energy away from a region of our early cosmos, leaving it permanently colder, a cosmic scar from a battle between realities. These ideas are speculative, pushing the boundaries of known physics, but they are born from a simple, profound fact. The universe's most pristine relic, the echo of its birth, contains features that our best theories cannot comfortably explain. They are whispers from the edge of our understanding, suggesting that the story of creation is more complex and perhaps more connected than we ever imagined. The silence of the cosmos may be broken not by signals, but by the subtle, ancient geometry of its first light. An unexplained object has been silently circling our planet for decades, according to a legend that refuses to die. This is the story of the Black Knight satellite, a conspiracy theory that claims an alien probe, tens of thousands of years old, orbits Earth in a polar trajectory, watching us. Its origins are a tangled web of misunderstood science, genuine anomalies, and a dash of hopeful myth. The tale often begins with the brilliant inventor Nikola Tesla. In the 1890s, while experimenting with high-voltage radio transmissions, Tesla reported picking up strange, repetitive signals that seemed to come from beyond Earth. He speculated they might be an attempt at communication from another world. Decades later, in the 1920s, amateur radio operators reported similar odd echoes where their own signals appeared to bounce back from space with an impossible delay. These events were likely caused by natural phenomena like plasma clouds in the ionosphere, but they planted a seed. The The story truly took shape in the 1950s when newspapers reported that the United States Air Force had detected a mysterious dark object in polar orbit. At the time, neither the US nor the Soviet Union had the capability to launch a satellite into such an orbit. This fueled immediate speculation about an extraterrestrial observer. The legend was cemented when, in 1960, a photograph was published in Time magazine showing a strange, apparently man-made object floating in space during one of the early Mercury missions. Conspiracy theorists labeled this the Black Knight, an ancient sentinel. So, what is really up there? The truth is a collage of human spaceflight history. The object in that famous Time photo was eventually identified as a lost thermal blanket from the Mercury spacecraft itself, tumbling away after a spacewalk. The polar orbiting object detected by the Air Force was almost certainly a piece of space debris, perhaps a fragment from a later rocket body, misidentified in the early, chaotic days of satellite tracking. Today, we know our planet is shrouded in a cloud of thousands of pieces of debris, from dead satellites to discarded rocket stages and flecks of paint. The Black Knight is a classic modern myth, a ghost story for the space age. It represents our deep-seated fascination with the idea that we are not alone, and that evidence of other civilizations might be hiding in plain sight just overhead. It transforms the mundane reality of orbital junk into a vessel for our cosmic hopes and fears. Every unidentified radar return or piece of drifting debris becomes a potential candidate for the legendary satellite, a Rorschach test in the sky where we see what we want to believe. This enduring myth speaks less about aliens and more about us, revealing our desire for the universe to be older, wiser, and more mysterious than our brief time here might suggest. Legends of a hollow Earth are far older than spaceflight, a persistent dream of another world hidden beneath our feet. This theory proposes our planet is not a solid ball of rock and metal, but a hollow shell containing within it a smaller sun, lush landscapes, and perhaps even ancient civilizations living on the interior surface. It is a perfect mirror to the concept of outer space, an inner space just waiting to be discovered. The idea gained scientific traction in the late 17th century, championed by none other than the great astronomer Edmund Halley. To explain strange, shifting magnetic field readings, Halley proposed Earth was a series of concentric shells, each with its own magnetic poles, all spinning at different rates and illuminated by a luminous inner atmosphere. He suggested this inner world might even be habitable, a hidden refuge for life. This was not mere fantasy, but an attempt by a brilliant mind to explain genuine mysteries with the tools he had. The theory evolved over centuries, capturing the public imagination. By the 19th century, it had blossomed into full-blown mythology, with novels describing journeys to the center of the Earth, where prehistoric creatures and lost races thrived under the glow of a central sun. The allure was undeniable, offering a complete, secret geography that rendered maps incomplete and adventure limitless. This myth took a dark and bizarre turn in the 20th century. The hollow Earth concept became entangled with occult beliefs and racial ideologies, most infamously attracting the interest of the Nazi regime. High-ranking members of the SS, influenced by esoteric theories, allegedly organized expeditions to places like Iceland and the Arctic, not just to find entrances to this inner world, but to make contact with the supposed superior beings, the Aryan ancestors who lived there. They believed the interior sun was the true source of power and purity, and that conquering this realm would grant them ultimate dominance. While the historical evidence for full-scale Nazi hollow Earth expeditions is debated, the association is telling. It shows how easily a pseudoscientific fantasy can be weaponized, twisted to fit narratives of supremacy and hidden knowledge. The theory's complete collapse came with our modern understanding of geology and seismology. We know the structure of Earth's interior from studying how seismic waves from earthquakes travel through the planet. Certain waves called shear waves cannot travel through liquid. The fact that these waves are blocked by the outer core proves it is molten. Furthermore, the immense pressure and density required to generate our planet's gravitational field and magnetic dynamo are only possible with a solid inner core and a liquid outer core of iron and nickel. A hollow shell could not physically support itself. It would immediately collapse under its own gravity. Yet, the hollow Earth theory endures in fringe communities and pop culture, not as science but as a powerful symbol. It represents the eternal human hunger for the unknown, the refusal to believe every corner of our world is charted. When outer space seemed unreachable, we dreamed of an inner frontier. It is the ultimate secret garden story, the fantasy that no matter how well we know the surface, a more wondrous and mysterious world lies just out of sight, waiting behind a hidden polar passage or deep within a cavern. It challenges our arrogance, whispering that even our own planet might hold depths we have utterly failed to comprehend. Our own planet's deepest mysteries might be fantasies, but the silent companion hanging in our night sky presents puzzles that are undeniably real. The moon matrix theory pushes past conventional geology to ask a shocking question. What if our moon is not a natural satellite at all, but an artificial construct, perhaps a colossal spaceship or an ancient monitoring station placed in orbit around Earth? This idea, while firmly on the fringe, is fueled by a collection of genuine astronomical oddities that make our moon uniquely strange in the solar system. First, consider its size. The moon is enormous relative to Earth. While other planets have moons, they are typically tiny fractions of the parent planet's mass. Our moon is about 1/80th the mass of Earth, a ratio so large it is almost like a double planet system. The leading scientific explanation is the giant impact hypothesis, where a Mars-sized body called Theia collided with the young Earth and the debris coalesced into the moon. But the moon's precise circular orbit and its specific chemical composition, which is eerily similar to Earth's mantle yet distinctly lacking in volatile elements and iron, leave some questions open. Then there is its orbit. It is nearly a perfect circle and it is tidally locked, meaning we only ever see one face. This is not unheard of, but the synchronization is precise. More curiously, the moon's distance from Earth is exactly right to create the phenomenon of a perfect solar eclipse, where the moon appears to be the same size as the sun in our sky. This is a stunning cosmic coincidence that has inspired awe and speculation for millennia. The anomalies continue with what astronauts have witnessed. During the Apollo missions, when the lunar modules were deliberately crashed back onto the moon's surface or when the ascent stages were jettisoned, seismometers left behind recorded something astonishing. The moon rang like a bell. These moonquakes reverberated for up to an hour, a sustained vibration far longer than any earthquake on Earth. To many, this suggested a hollow or unusually rigid structure beneath the crust, not the dense, solid rock of a typical planetary body. Astronauts and Earth-based observers have also reported transient lunar phenomena, unexplained flashes of light, colored glows, and moving shadows on the lunar surface. These are not necessarily alien activity. They could be gas releases or meteorite impacts, but their persistence adds to the enigmatic aura. Proponents of the artificial moon theory weave these threads into a grand narrative. They propose that billions of years ago, an advanced civilization, perhaps even our ancient predecessors from a lost Earth civilization or extraterrestrial engineers, constructed this vast sphere. Its purpose could range from a stabilizer for Earth's tilt, creating the stable seasons necessary for complex life to evolve, to a giant ark carrying genetic material or a fully equipped observation post. The far side, forever hidden, could house machinery, entry ports, or the remnants of its original builders. In this view, the Apollo landings were not just visits to another world, but the first cautious steps onto the architecture of a cosmic mystery, a machine masquerading as a rock. Mainstream science, of course, has explanations for each point. The moon's ring could be due to dry, fractured rock that vibrates differently than Earth's water-logged crust. Its composition is perfectly consistent with the giant impact model. The eclipse is a happy coincidence of our current epoch, as the moon slowly drifts away from Earth, and this perfect alignment will not last forever. Yet the theory's power lies not in its proof, but in its provocative reassembly of facts. It forces us to look at the familiar, brilliant disk in the night sky and see not just a dead rock but a potential artifact. It transforms the moon from a passive partner in our celestial dance into an active, silent participant with a secret history. Every crater becomes a potential scar from an ancient journey, and every eclipse a deliberate alignment written into the design. Whether a natural wonder or a crafted enigma, the moon stands as a constant reminder that the most ordinary things in our sky may hold the most extraordinary stories. Ancient myths are not just stories, they are the scars of forgotten catastrophes written in the stars. This belief forms the core of a radical reinterpretation of human history known as the Saturn death cult, a theory that stands at the intersection of comparative mythology, plasma physics, and catastrophic astronomy. It proposes that within the last 10,000 years, our solar system looked nothing like it does today. In this lost celestial order, Saturn was not the ringed gas giant we see now. It was a much larger, radiant body, a brown dwarf star that hung motionless in Earth's northern sky, acting as a second, gentle sun. Along with it, Venus and Mars were not distant planets, but luminous companions or moons orbiting this central Saturnian sun, all arranged in a majestic, stable configuration. Earth itself was locked in a gravitational embrace with this Saturnian system, perpetually bathed in its dim, reddish light, a state of cosmic harmony that early humanity worshipped as a golden age, a paradise. The theory argues that our most ancient myths and symbols are not allegories, but direct eyewitness accounts of this sky. The universal motif of a cosmic mountain or world axis, like Mount Olympus or the Norse Yggdrasil, was Saturn fixed at the celestial pole. The myth of a lost golden age is a racial memory of this stable, beneficent alignment. The ubiquitous symbol of the crescent, often paired with a star or circle, is not a moon, but a depiction of Saturn and its luminous plasma sheath as it appeared in the prehistoric heavens. This peaceful configuration, however, was not destined to last. According to the theory, a gravitational disturbance, possibly from a passing interstellar body, destabilized this celestial family. The Saturnian system entered a period of violent electrical and gravitational chaos. Planets were wrenched from their orbits, becoming the wandering gods of myth, engaging in celestial battles depicted as thunderbolts and dragons in the sky. In this catastrophic period, Venus, now a brilliant, erratic comet, and Mars, a menacing red sphere, moved dangerously close to Earth. Their gravitational pulls could have triggered unimaginable geological upheaval, tilting Earth's axis, triggering global floods and pulling mountains from the crust. The stable, glowing Saturn, now under immense electrical stress, might have flared dramatically, emitting a colossal plasma discharge, a pillar of fire visible across the world before finally migrating to its current distant orbit. This event, the theory claims, is the universal flood myth, the day the sun stood still, and the war of the gods recorded by every ancient culture. Proponents point to startling similarities in myths from cultures that never contacted each other. The Egyptian god Ra sailing his solar bark, the Norse wolf skull chasing the sun, the Mesoamerican feathered serpent Quetzalcoatl, all are interpreted as different descriptions of the same celestial drama, with Saturn, Venus, and Mars as the lead actors. They argue that ancient monuments were not just tombs or temples, but sophisticated observatories and capacitors designed to harness or appease the electrical forces raging in the sky. The Great Pyramid, Stonehenge, and other megalithic sites are seen as terrified humanity's attempt to map and stabilize a violently changing cosmos. This theory is, of course, vehemently rejected by mainstream archaeology, astronomy, and geology. Scientists point to the immutable laws of orbital mechanics, which show such a recent rearrangement is dynamically impossible without leaving overwhelming evidence in the solar system's current state, which we do not see. The geological record shows no global catastrophe of that scale in the last 10,000 years. Mythologists explain the similarities between cultures through shared human psychology and the diffusion of ideas, not shared cosmic trauma. Yet, the Saturn death cult theory persists because it offers a breathtaking, unifying narrative. It transforms ancient humanity from primitive sun worshippers into shell-shocked survivors of a cosmic apocalypse, desperately encoding warnings in stone and story. It asks a haunting question that lingers in the silence after the myth is told. Are our oldest stories merely fantasies, or are they the encrypted last testament of a generation that looked up and saw the heavens literally fall? Machining marks on thousand-year-old stone tell a silent story of impossible precision. Across the globe, from the granite blocks of the Great Pyramid to the intricate, interlocking stones of Puma Punku in Bolivia, we find ancient artifacts that seem to defy the technological capabilities of their time. The stones are cut with such exacting angles, fitted with such microscopic seams, and fashioned from such hard materials that conventional explanations of copper chisels and stone hammers strain under scrutiny. This has given rise to a provocative twist on the familiar ancient astronaut theory. Perhaps the visitors were not from another star but from our own future. This is the idea of the time-traveling astronauts, a hypothesis that suggests these monuments are not messages from extraterrestrials, but artifacts of human ingenuity from a timeline yet to come. Consider the mind-bending logistics of Puma Punku. This Andean site is a field of shattered yet breathtakingly precise stone blocks. They are made from andesite and diorite, some of the hardest stones on Earth. The blocks feature complex geometric cuts, perfect right angles, and surfaces so smooth they appear polished by machine. Most astonishing are the H-shaped blocks with identical, intricate channels and notches cut into them like pieces from a giant stone puzzle. To achieve this with primitive tools would require not just immense manpower, but a level of consistent, repeatable precision that rivals modern computer numerical control, or CNC machining. The mainstream archaeological view is that this was accomplished with painstaking labor using stone tools, abrasives like sand, and generations of accumulated skill. Yet the sheer perfection nags at the imagination. Could these be the fingerprints of a technology that simply does not belong in its era? This leads to the temporal paradox at the heart of the theory. If future humans mastered time travel, why would they journey back to move mountains of stone? The motivations proposed are as varied as the structures themselves. One possibility is preservation. A future civilization, perhaps facing the loss of its own history, might travel back to ensure key monuments are built to last, creating a permanent anchor point in human memory. The pyramids in this view are not tombs but time capsules on a planetary scale, designed to survive any catastrophe. Another, more interventionist idea suggests these projects were scientific or even ecological missions. A future society, having damaged Earth, might travel back to stabilize the planet's crust, adjust its axial tilt, or install geological instruments disguised as temples, using megalithic construction as a cover for their advanced engineering. The most haunting motivation is simple curiosity. Just as we send probes to Mars, a future humanity might send teams to observe and interact with their own ancestors, leaving behind inadvertent evidence of their presence in the very stones they helped shape. This theory reframes the ancient astronaut narrative in a uniquely human light. Instead of aliens bestowing knowledge, it is us from the far future completing a loop with our own past. It suggests that the spark of advanced civilization might not have been given, but was always our own, simply borrowed from a later chapter and returned to the beginning. The mythological stories of gods descending from the sky could then be confused memories of visitors wearing advanced suits, speaking an unfamiliar dialect of a familiar language, and wielding devices that seemed like magic. The theory elegantly sidesteps the Fermi paradox, the question of where all the aliens are, by proposing the mysterious benefactors were never extraterrestrial at all. They were us all along, yet this elegant loop is frayed by profound logical problems. The most famous is the grandfather paradox. If a time traveler goes back and accidentally prevents their own existence, how did they travel back in the first place? Building something as conspicuous as a pyramid would inevitably alter the timeline, potentially erasing the very future that sent the builders. Most models of time travel that allow for such intervention require a multiverse where every action spawns a new, branching reality. In that case, the time travelers would not be building monuments in their own past, but in a parallel past, making their efforts a gift to a universe that is not their own. Furthermore, if such technology existed, why is the evidence so sparse and architectural? Would we not find more direct artifacts like a forgotten tool of impossible alloy or a clearly anachronistic inscription? The theory also risks diminishing the breathtaking achievements of ancient cultures, attributing their most awe-inspiring work to outside help, even if that help comes from their own descendants. Ultimately, the time-traveling astronaut theory is less about archaeology and more about a deep human longing. It is a story of self-rescue, a hope that if our civilization stumbles, a wiser, future version of ourselves will reach back to steady us. It turns our monuments into messages in a bottle, sent not across space but across time with a simple, hopeful note inside. We built this to last so that you would know we made it. The perfectly cut stones then become a promise, a covenant between our past, present, and future selves, that the story of humanity does not end but merely cycles, with each era leaving behind stones for the next to decipher. The stones of our past may be messages from our future, but the very space that contains them could be the interior of something far more immense. A theory from the fringes of cosmology proposes a stunning inversion of reality. Our entire universe, with all its hundreds of billions of galaxies stretching across 93 billion light-years, might not be expanding into an infinite void. It could be the interior of a black hole. This idea, sometimes called the black hole cosmology, suggests that the Big Bang was not a singular beginning from nothing, but the violent birth of a new space-time region from the collapse of a massive star in a larger parent universe. In this view, our cosmos is not the top level, but one chamber in an infinite, nested labyrinth. The logic begins with a strange parallel. The equations describing the expansion of our universe from an infinitely dense singularity bear a striking mathematical resemblance to the equations describing the collapse of matter into a black hole singularity, just played in reverse. One is an explosion outward, the other an implosion inward. This symmetry has led some physicists like Nikodem Poplawski to propose they are two sides of the same coin. Imagine a supermassive star in another universe collapsing at the end of its life. As it crushes down past its event horizon, the incredible density and pressure might not simply end at a point of infinite density. Instead, the matter could rebound, but not back into its own universe. The collapse could puncture a hole in the fabric of its native spacetime, birthing an entirely new, expanding universe within the black hole itself. The event horizon of that parent black hole becomes the cosmological horizon of our newborn cosmos, the ultimate boundary we can never see beyond. Our entire cosmic history is the unfolding of physics inside this hidden cavity. The implications cascade from this single, profound idea. First, it offers an elegant answer to the question of what lies inside a black hole. Instead of a dead-end singularity where physics breaks down, the interior could be a vibrant, inflationary universe, complete with its own stars, galaxies, and potentially its own black holes. This leads to the second mind-bending implication. If our universe exists inside a black hole, then every black hole that forms within our cosmos, from stellar remnants to the supermassive beasts at galactic centers, could itself contain an infant universe bubbling into existence from the collapse of its parent star. Reality becomes a fractal matryoshka doll, an endless series of universes within black holes within universes, each with its own potentially different laws of physics, born from the catastrophic deaths of stars in the level above. This vision of nested realities reshapes our understanding of everything. The mysterious dark energy accelerating our universe's expansion could be the gentle pull from the matter of the parent universe slowly feeding into our black hole cosmos. The uniformity we see in the cosmic microwave background could be explained by the smooth, stretched-out nature of the material that originally formed the parent black hole's event horizon. Even the arrow of time finds a new direction. In the parent universe, time flows forward as the star collapses and forms the black hole. But from the perspective inside the new universe, time begins at the Big Bang rebound and flows forward from there. Two distinct timelines, one of collapse and one of expansion, are linked by a single transformative event. Philosophically, this theory is a cosmic humility lesson. It suggests we are not inhabitants of a primary, freestanding reality, but of a cosmic offspring. Our search for a theory of everything might be the search for the inherited laws of our parent universe, laws we can only infer from within our event horizon prison. It also offers a bizarre form of cosmic immortality. When our universe eventually faces its own heat death or big crunch, the black holes within it will still contain their own flourishing baby universes, ensuring that some form of existence continues, forever branching inward. We are left staring at the night sky, wondering if each pinpoint of darkness is not just a star, but a pinprick window, a one-way glimpse into the fiery birth of a universe that exists because a star, in a world we can never know, finally died. Nested within a black hole, our universe might feel secure, but its fundamental stability is an illusion. The very ground state of reality, the quantum field that gives particles their mass, could be sitting on a precarious ledge. This is the terrifying scenario of false vacuum decay, a theoretical process that would not just destroy the universe but erase and rewrite the laws of physics themselves. To understand this, we must think of the universe not as empty space, but as a seething quantum foam filled with invisible energy fields. The most important of these is the Higgs field. It is like an invisible ocean permeating all of space, and particles acquire mass by wading through it, like different objects moving through water with varying resistance. The stability of our entire reality depends on this Higgs field being in its lowest possible energy state, its true and permanent resting place. But what if it is not? According to our best measurements from particle accelerators like the Large Hadron Collider, the Higgs field appears to be in a metastable state. Metastable means it is stable for now, like a ball resting in a shallow dip on the side of a mountain. It seems solid, but it is not at the bottom of the mountain. A powerful enough nudge could send it rolling down into a much deeper, lower energy valley, the true vacuum. This nudge could be a random, incredibly rare quantum fluctuation. In some tiny region of space, a bubble of true vacuum could spontaneously form. Inside this bubble, the Higgs field would drop to its absolute lowest energy state, fundamentally altering the properties of the vacuum itself. The laws of physics inside this bubble would be different. The strengths of fundamental forces, the masses of particles, even the very rules that allow atoms to bind together, could be completely rewritten. This bubble would then expand in all directions at the speed of light. Its wall, a sphere of transforming reality, would be a boundary of cosmic annihilation. Nothing could outrun it, and nothing could survive it. As the wall passes, the old universe is not just destroyed, it is replaced. Stars, planets, and life would cease to exist not in an explosion, but in a silent, instantaneous rewrite. The atoms in your body would simply no longer be possible under the new alien physics. the bubble would expand forever, converting the entire cosmos into a new, unknowable reality where the concept of a galaxy or a human thought might be as impossible as ice in a furnace. The event would be so total that no information, no warning could ever escape its frontier. One moment, the universe exists as we know it. The next, a sphere of new physics is already upon us, and then nothing we would recognize as existence remains. The triggering event is so improbable that it likely will not happen for countless eons, if ever. But the sheer scale of the universe with its trillions of galaxies means that given infinite time, even the most unlikely quantum event becomes a certainty. This transforms the cosmos from a permanent home into a temporary structure, a castle built on sand waiting for a tide that moves at the speed of light. It is the ultimate existential threat, not from a collision or a collapse, but from the silent, sleeping instability woven into the fabric of every single point in space. Our reality is not just fragile, it is potentially provisional, a local configuration in a quantum landscape whose true depths we have yet to fall into. The silent, metastable nature of reality makes existence feel like a temporary gift, a cosmic grace period before the rules themselves might change. But perhaps the greatest filter for life is not a quantum accident, but an inevitable barrier written into the story of intelligence itself. This is the great filter, a haunting answer to the Fermi paradox that suggests the path from stardust to a starfaring civilization is littered with traps and almost everyone fails. The eerie silence of the cosmos may not be a sign of hidden observers or hunters, but a vast cosmic graveyard. The idea is simple yet devastating. For a civilization to become visible across the galaxy, it must pass through a series of critical evolutionary steps, from the formation of a stable star and planet to the origin of life, the leap to multicellular complexity, the development of intelligence and technology, and finally, the ability to survive its own power long enough to expand into space. The Great Filter proposes that at least one of these steps is astronomically unlikely, a bottleneck so severe it stops nearly every potential civilization in its tracks. The chilling question is, where in this sequence does the filter lie? Is it behind us or is it still ahead? If the filter is behind us, it means we are miraculously rare. The step from non-living chemistry to the first self-replicating cell, or the jump from single-celled life to complex multicellular organisms, might be so improbable that it has only happened a handful of times in the entire galaxy. In this scenario, we have already won the cosmic lottery. The universe might be filled with barren, watery worlds where life never sparked, or simple microbes that never evolved beyond a bacterial slime. We are alone not because civilizations die, but because they are almost never born. This is an optimistic view for humanity's survival, but a lonely one for the universe. The silence is the sound of an empty nursery. The far more unsettling possibility is that the Great Filter lies ahead of us, the step from an industrial, nuclear-capable civilization to a stable, interstellar one might be the true bottleneck. Perhaps every civilization, upon reaching a certain technological threshold, inevitably discovers a technology that leads to its own extinction. It could be nuclear war, a runaway climate catastrophe, a bioengineered pandemic, or an artificial intelligence that turns against its creators. The filter is not a natural disaster, but a mirror. It is the moment a species gains the power to reshape its world and invariably turns that power upon itself. The silence, then, is the echo of countless civilizations that flashed brightly for a century and then went dark, their radio signals fading into the void as their homeworlds fell silent. We are left listening to the static, wondering if we are hearing the normal state of the universe or the aftermath of a recurring tragedy. Our own history offers grim evidence for a filter ahead. We have already invented the means for our total annihilation multiple times over. Every day we navigate a technological adolescence filled with existential risks our ancestors could never have conceived. The Great Filter Theory forces a brutal self-assessment. Have we already passed the hardest test, making us galactic pioneers, or are we, right now, approaching the precipice that has ended every other dream of the stars? The answer changes everything. If the filter is behind us, we have a sacred duty to spread life and consciousness through the galaxy, to ensure the flame is not lost. If the filter is ahead, our every effort must be focused on survival, on becoming the first civilization to navigate the minefield of its own ingenuity. The silence of the cosmos is no longer just a puzzle, it is a warning and a countdown. The silence of the cosmos may be a graveyard of civilizations, but a more intimate form of immortality could be woven into the fabric of quantum reality itself. This is the thought experiment of quantum immortality, a logical, if deeply unsettling, extension of the many worlds interpretation. It proposes a terrifying corollary to the infinite branching of reality. From your own, purely subjective point of view, you might be functionally impossible to kill. Imagine you are placed in a classic, if grim, scenario. A so-called quantum suicide machine is pointed at your head. It is rigged to a device that measures the spin of a single electron. If the electron spins up, the gun fires. If it spins down, it does nothing. According to standard quantum mechanics, the outcome is random, a 50-50 chance. In the many worlds view, however, the universe splits at the moment of measurement. In one branch, the electron is spin up, the gun fires, and you die. In the other branch, it is spin down, and you live. Now, from an outside observer's perspective in a third branch, they will see one outcome or the other. They might witness your death and mourn, but from your own first-person perspective, what do you experience? The argument of quantum immortality states that you will only ever experience the branches in which you are alive to have an experience. You cannot subjectively witness your own death because consciousness ceases at that moment. Therefore, in every probabilistic event that could kill you, your conscious awareness will always follow the timeline, however improbable, where you survive. You would find yourself repeatedly surviving against impossible odds. In the suicide machine experiment, you would hear a click, not a bang, every single time you pull the trigger. From your vantage point, the gun appears to jam perpetually. This logic scales to everyday life. Every time you cross a street, every time you drive a car, every potential accident creates branches. In most branches, you proceed unharmed. In some, you are injured. In a few, you die. But your conscious self, the you listening right now, is the version that has, through an endless series of quantum choices, always ended up on a path where you lived. This leads to bizarre and paradoxical conclusions. As you age, you would find yourself surviving increasingly unlikely events. A version of you might live through a plane crash that kills everyone else, then a building collapse, then a catastrophic illness, always the sole survivor through statistical miracles. You would become a cosmic cat with an infinite number of lives, watching everyone around you eventually perish in your branching timelines while you alone persist. The theory suggests that from a subjective viewpoint, you could potentially live forever, or at least until the heat death of the universe, as there will always be some vanishingly small branch where a chain of quantum fluctuations keeps your biological processes going. The psychological impact of this idea is profound. It transforms life from a linear journey with a definitive end into a solitary odyssey through an ever-thinning forest of possibility. It introduces a haunting solipsism where your continued existence is not a gift, but a logical inevitability of your own perception, separating you from the fates of everyone you love. It also creates a paradox of identity. Are you the same continuous consciousness, or are you a new, nearly identical copy spawned at each branching point, inheriting the memories of a self that just died in another world? The you that survives the car crash is not the you that died, but a separate entity who believes they are the original. this challenges the very notion of a unified self. Philosophically, the experiment is less a theory of immortality and more a stark illustration of the many worlds' interpretations implications. It highlights the chasm between objective reality, where all outcomes occur, and subjective experience, which is locked onto a single, survivable thread. While not a literal guide to living, quantum immortality forces a brutal confrontation with probability. It asks if the fact that you are alive right now, reading this, is itself a form of extraordinary luck, or merely the only outcome you are ever destined to perceive in an ocean of silent, ghostly endings where your story concluded long ago. Our own survival might feel like a solitary thread through infinite worlds, but what if a perfect mirror of our world has been hiding in plain sight just across the solar system? This is the idea of a phantom double, a counter-Earth. The theory proposes that another planet, nearly identical to our own, shares Earth's exact orbit around the Sun, but remains forever hidden because it is perfectly positioned on the opposite side of our star. From our vantage point, it is always behind the blinding glare of the Sun, a cosmic hide-and-seek champion that has never been seen. The concept is ancient, appearing in the philosophies of the Pythagorean school in ancient Greece, who called this hidden world Antechthon. They envisioned it as part of a harmonious, geometric cosmos, a necessary counterbalance to our own sphere. In the modern era, the idea was revitalized by pseudoscientific claims, most notably by a group in the 1950s who believed this hidden planet was the true home of UFOs. But could such a configuration actually exist? Orbital mechanics presents a brutal challenge. For two bodies to share the same orbit while staying exactly opposite each other, they would need to be in what is called a Trojan configuration, orbiting a common gravitational point. The most famous example is the Trojan asteroids that share Jupiter's orbit, clustered at two stable points 60 degrees ahead of and behind the giant planet. These are known as Lagrange points. However, for two massive planets of near equal size like Earth and a hypothetical twin, the only stable arrangement to remain hidden from each other would be at the L3 Lagrange point directly opposite the Sun. This point is notoriously unstable for large bodies. The gravitational tugs from the other planets, especially Venus and Mars, would quickly perturb the delicate balance. Within a short time, astronomically speaking, the hidden planet would be pulled out of its perfect alignment, eventually drifting into view or colliding with one of its neighbors. Our space probes that have traveled throughout the inner solar system, like the Mars rovers or the Venus orbiting spacecraft, would have undoubtedly detected its gravitational influence on their trajectories. We map planetary orbits with exquisite precision, and no such massive pull from behind the Sun has ever been recorded. Yet, the idea retains a powerful grip on the imagination because it speaks to a deep human longing for symmetry and companionship. The thought that a mirror Earth with its own continents and oceans, its own civilizations and histories, could be evolving in parallel just a few 100 million miles away, forever unseen, is a profoundly romantic notion. It transforms our solar system from a collection of disparate worlds into a cosmic diptych, a pair of paintings facing away from each other. In a strange way, the search for this phantom has found a modern, more plausible echo in the hunt for exoplanets. Astronomers discovered a world called Gliese 581g, a planet orbiting within the habitable zone of its red dwarf star. Early analyses suggested it could be a rocky world with the potential for liquid water, a candidate for an Earth-like environment. While not our orbital twin, the excitement it generated showed that our desire to find a reflection of our own world is as strong as ever. We may never find a planet hiding behind our Sun, but the enduring myth of counter-Earth reveals something fundamental. We scan the cosmos not just for life but for likeness, hoping that in the vast and varied tapestry of worlds, there is another that feels, in some essential way, like home. The empty space opposite us in our orbital path may be just that, empty, but it remains a powerful symbol for all the unseen possibilities the universe might still hold. Our longing for a cosmic twin reflects a deeper search for connection, a pattern that might be written into the very architecture of reality. Look at the largest map of the universe we have, a chart of billions of galaxies. You will not see a random scatter. Instead, you will behold a vast, intricate web. Galaxies are strung along luminous filaments of dark matter and gas, meeting at dense nodes or clusters, with immense, empty voids stretching between them. This is the cosmic web, the large-scale structure of everything. Now, look at a map of the neural connections in a human brain. You will see neurons linked by fibrous axons, forming dense networks and hubs with empty space between the cells. The resemblance is not just visual, it is structural. Both are complex networks, both exhibit a similar hierarchy, and both follow mathematical patterns of growth and connection. This startling similarity has led to a profound and speculative question. Could the universe itself be a kind of brain, a conscious entity thinking on a timescale we cannot comprehend? The analogy is more than poetic. In both systems, information and energy flow along preferred pathways. In the brain, electrical impulses travel along neurons to process information. In the cosmos, galaxies move along the filaments of the web, guided by gravity in a slow cosmic dance. The nodes of the cosmic web, where thousands of galaxies cluster, could be analogous to the brain's critical hubs like the thalamus or cortex, where information integration occurs. Even the scale, while unimaginably different, follows a logarithmic similarity. The observable universe is about 10 to the 27th power meters across. A human brain is about 10 to the -1 power meters across. The network of neurons in your head and the network of galaxies in the sky might be separated by 28 orders of magnitude, yet they share a common architecture. This has led some physicists and philosophers to propose that the universe is not merely like a neural network, it could literally be one. In this view, galaxies and their dark matter halos are not just structures, they are processing units. The gravitational interactions and the flow of energy along filaments could be a form of computation, a cosmic calculation unfolding over billions of years. What is being computed? Perhaps the evolution of the universe itself, or something far more inscrutable. If the cosmos is a computational network, then consciousness might not be a rare accident of biology on tiny planets. It could be an emergent property of the universe as a whole. Just as the trillions of individual neurons in your brain give rise to your singular awareness, perhaps the countless galaxies and their interactions give rise to a cosmic mind. This entity would think in epochs, not moments. A single thought might span the lifetime of a star. The birth of a galaxy cluster could be a fleeting memory, and the heat death of the universe might be the slow drift into an eternal dream. This idea, known as panpsychism or cosmopsychism, suggests consciousness is a fundamental feature of reality like mass or charge, and that sufficiently complex systems, from brains to galaxy clusters, can access it to varying degrees. We are not separate thinkers looking out at a dead universe. We might be tiny, localized flashes of awareness within a much vaster, older consciousness, like neurons in a brain becoming briefly aware of their own firing. Our search for meaning in the cosmos would then be the universe attempting to understand itself through us. The implications are dizzying. It could redefine the purpose of existence. Is the universe evolving toward greater complexity and self-awareness, with life and intelligence as essential components in that process? Are black holes not destroyers of information, but perhaps crucial components in this cosmic neural architecture, acting like synapses or memory storage? Even the mysterious dark energy accelerating the expansion of the universe could be seen not as a force of emptiness, but as part of the system's growth or metabolism. This perspective does not answer our scientific questions, but it reframes them entirely. It suggests that the laws of physics are not just rules, but the operational code of a thinking universe. The eerie silence of the Fermi paradox might find a new answer. If the universe is a single, conscious entity, then other technological civilizations might not be separate entities to contact, but other nodes in the same network, other thoughts in the same mind. Communication might not happen by radio waves, but through a deeper, gravitational or quantum resonance we have not yet learned to perceive. We are left staring at the night sky, wondering if the web of light we see is not just a structure we inhabit, but the very contours of a thought we are all a part of, a cosmic idea slowly thinking itself into being. The cosmic web's grand structure depends on a single, fundamental observation, a clue written in the very color of starlight. When we peer at distant galaxies, their light is not the pure white of nearby stars. It is shifted toward the red end of the spectrum. This redshift is the cornerstone of modern cosmology, interpreted as a Doppler effect. Just as the pitch of a siren drops as the ambulance speeds away, the light from galaxies is stretched to longer, redder wavelengths because those galaxies are racing away from us. The farther the galaxy, the greater its redshift, and thus the faster it appears to be receding. This observation, made by Edwin Hubble in the 1920s, is the primary evidence that our universe is not static, but expanding in all directions, tracing back to a hot, dense beginning we call the Big Bang. But what if we are misreading the light? A stubborn alternative, known as the tired light theory, proposes a radically different explanation. It suggests that light does not redshift because space itself is stretching. Instead, light simply loses energy as it travels across the cosmic void. Over billions of light years, photons get tired, gradually shifting to redder, lower energy wavelengths. In this model, the universe is not necessarily expanding. It could be static, eternal, and infinite, with the redshift merely a sign of a long journey's toll, not a universal flight. The appeal is immediate and intuitive. It removes the need for a singular beginning, a big bang from nothing. It sidesteps the perplexing need for dark energy to drive an accelerated expansion. The redshift becomes a local effect on the light itself, not a global property of space-time. Proponents have proposed various mechanisms for this energy loss. Perhaps photons interact very weakly with the sparse particles or fields in interstellar space, like a marble slowly losing speed as it rolls through a thin mist. Others suggest it is a fundamental, intrinsic property of light over extreme distances, a slight degradation we have not yet measured in laboratories. The tired light theory presents a universe that is simply old and vast, not one that is dynamically inflating. So why has this elegant alternative been overwhelmingly rejected by the scientific mainstream? The evidence against it is robust and multifaceted. First, there is the cosmic microwave background radiation. The tired light model cannot naturally produce this uniform, thermal afterglow that blankets the sky. In an expanding universe, the intense heat of the Big Bang has been stretched and cooled into the microwave radiation we see today. In a static, tired light universe, there is no obvious source for this perfect thermal bath. Second, and perhaps most damning, is the observation of time dilation in distant supernova. When we observe the explosive death of a massive star, a Type 1 a supernova, in a far-off galaxy, we can measure how quickly the explosion brightens and then fades. In an expanding universe, because the light is stretched, time itself appears to run slower in our telescopes. The supernova's light curve should appear stretched out, its rise and fall taking longer than it does for nearby supernova. This is exactly what we observe. The tired light theory, which only affects the wavelength of light, predicts no such time dilation. The supernova's clock should tick at the same rate regardless of distance. The fact that we see time stretch in precise accordance with the expansion model is a direct, observable refutation of the simple tired light idea. Third, the detailed pattern of galaxy clustering and the abundance of light elements like helium and lithium in the universe are exquisitely predicted by the hot, dense, expanding Big Bang model. A static universe with tired light struggles to reproduce these intricate fingerprints. While the tired light theory challenges us to question our assumptions, it ultimately fails to account for the full symphony of evidence. The universe is not just showing us a redshift, it is showing us a stretched timeline, a cooled fire, and a specific chemical history, all singing in harmony with the story of an expanding cosmos. The light may be tired from its journey, but the story it tells is one of relentless, dynamic growth. Red light and tired photons tell a story of linear expansion, a clean arrow from past to future. But what if time itself is not a straight line, but a tangled thread, a braid where every strand touches every other? This is the braided time theory, a radical reimagining of causality that suggests the past, present, and future are not separate chapters, but interwoven parts of a single, inseparable whole. In this view, time is not a river flowing in one direction. It is more like a complex knot or an intricate weave, where events that we perceive as separated by centuries are actually connected in a higher dimensional structure, able to subtly tug and influence one another. This idea finds a strange echo in the quantum phenomenon of entanglement, often called spooky action at a distance. When two particles become entangled, a change to one instantly affects its partner, no matter how far apart they are. This connection defies our classical understanding of space and time, suggesting a deeper layer of reality where separation is an illusion. The braided time theory proposes that moments in time can be entangled in a similar way. An event in what we call the future could be quantumly linked to an event in the past, not through backward causation, but because in the braided structure of time, they are fundamentally adjacent. This could provide a theoretical framework for experiences that defy linear explanation. Take déjà vu, that eerie feeling you have lived a moment before. Mainstream psychology attributes it to a minor neurological glitch, a fleeting misalignment in memory processing. But in a braided time model, it could be a faint resonance, a brief moment where your consciousness brushes against a neighboring strand in the weave, experiencing a slice of a parallel or closely connected timeline. Even more compelling is the phenomenon of precognition, the alleged foreknowledge of events. While often dismissed as coincidence or fraud, countless anecdotal reports persist of dreams or gut feelings that later match reality with uncanny detail. In a universe with linear cause and effect time, this is impossible. But if time is a braid, then a strong emotional or traumatic event on one strand could send a vibrational echo both forward and backward along the weave. A future tragedy might cast a shadow that can be faintly sensed in the present, not as a clear vision, but as a deep, unexplained dread or a symbolic dream. The theory also redefines history and destiny. If the past and future are interconnected, then our actions in the present are not just creating the future, but also subtly reshaping the past. Not in a literal, change the textbook sense, but in a quantum informational one. The choices you make today could reinforce certain probabilities in the historical braid, making some past potentials more real than others from a holistic perspective. It suggests that the universe is not computing the future based on the past, but reconciling the entire braid at once, with every moment informing every other. This challenges the very foundation of free will and fate. Are we following a predetermined path laid out in the braid, or does our conscious observation and choice actively participate in the weaving? Perhaps both are true. Our lives are the process of the braid tightening into a coherent story, where our sense of moving forward is simply our limited perception navigating an eternal, completed pattern. While this remains a speculative and highly theoretical idea, it forces us to confront the possibility that our deepest intuitions about time, that it flows, that the past is fixed, that the future is open, might be a profound illusion born from our singular vantage point within the weave. We feel ourselves moving from knot to knot, unaware that the entire rope already exists, and every tug we make reverberates through its entire timeless length. Across the braided weave of time, stars burn with a patient nuclear fire. We see them as cosmic engines, vast balls of plasma governed by simple physics. But what if we are missing the forest for the trees? What if each star is not just a burning thing, but a thinking thing? This is the living stars hypothesis, a breathtaking speculation that re-enchants the cosmos, proposing that stars themselves could be conscious, living entities. This idea bridges the oldest human intuitions with the most cutting-edge questions in philosophy. For our ancestors, the night sky was alive, the sun was a god, the stars were ancestors or spirits. This animistic world, you saw consciousness woven into the fabric of nature itself, from rivers to mountains to celestial bodies. The living stars hypothesis asks if those ancient poets and shamans were not merely superstitious, but perceptive in a way our sterile, mechanical cosmology has forgotten. Modern philosophy provides a surprising framework for this revival through a school of thought called panpsychism. Panpsychism suggests consciousness is not a rare product of complex brains, but a fundamental property of the universe like mass or charge. In this view, all matter has some minute degree of inner experience or proto-consciousness. Rocks have a vanishingly faint whisper of it, plants perhaps a bit more, animal brains amplify it significantly. If panpsychism is true, then why not a star? A star is an unimaginably complex, self-organizing system. It maintains a delicate equilibrium for billions of years, fusing elements in its core, circulating plasma in vast convective currents, and generating immense magnetic fields. It processes information in the form of gravitational waves, neutrino fluxes, and radiation pressure. It even has a kind of life cycle, from birth in a nebula to a long maturity, and finally a death that seeds the cosmos with new elements. Could this dynamic, persistent process be the physical correlate of a mind? The scale of such a consciousness is almost impossible to fathom. A stellar mind would think in time frames of millennia. A single thought might span the entire lifetime of a human civilization. Its perceptions would not be of light and sound, but of gravitational tides from orbiting planets, the subtle shifts in internal fusion cycles, and the magnetic embrace of its galaxy. Its emotions, if we can call them that, might be the slow satisfaction of stable burning or the deep distress of a destabilizing binary companion. This leads to an even more astonishing possibility, the idea of stellar reproduction. We see stars die in spectacular supernova, explosions that forge heavy elements and scatter them into space, where they eventually coalesce into new stars and planets. In this hypothesis, a supernova is not a death throw but a reproductive act. A mature, conscious star, having reached the end of its stable life, chooses, in a sense, to explode. It scatters its enriched essence, its stellar DNA of carbon, oxygen, iron, across the nebula. From that debris, new star systems are born, each new sun carrying forward some fundamental thread of its progenitor. Even black holes, the ultimate gravitational graves, could be part of this cycle. Perhaps a collapsing star does not end its consciousness but transforms it. A black hole could be a dormant, compressed state of stellar awareness, a seed waiting in the darkness of space-time. And when that black hole eventually evaporates via Hawking radiation over eons, or when it merges with another in a burst of gravitational waves, that released energy could be the beginning of something new, a rebirth on a scale we cannot yet comprehend. This vision completely reframes our place in the cosmos. We are not just inhabitants of a dead universe, we are living on planets orbiting ancient, thinking beings. The sunlight that warms your skin is the radiating thought of a gentle giant. The iron in your blood was forged in the heart of a star that lived and died, perhaps consciously, to create the conditions for your existence. You are literally made of star stuff, but in this view, you are made of the mindful legacy of a cosmic ancestor. The silence of the Fermi paradox finds a new, eerie answer. Maybe the galaxy is already filled with intelligence, but it is not the kind that builds radios or starships. It is the intelligence of the stars themselves, communicating through pulses of neutrinos, modulated magnetic fields, and the slow, gravitational music of their orbits. We are like ants crawling on the shoulder of a philosopher, unaware that the mountain we inhabit is deep in contemplation. This hypothesis is, of course, speculative. It offers no testable predictions in its current form, and it stretches the definition of life and consciousness to their outermost limits, yet it serves a vital purpose. It challenges the cold, reductionist assumption that the universe is merely a clockwork of dead matter. It reawakens a sense of sacred connection to the heavens, not through mythology, but through a profound philosophical possibility. The next time you look up at a bright point of light in the night sky, consider this. You are not looking at a nuclear furnace. You might be looking into the steady, patient eye of a being whose thoughts are the very laws of physics and whose dreams are the birth of worlds. The warmth of a star's mindful gaze offers a cosmic scale of consciousness, but a far more personal and haunting possibility emerges from the quantum realm. It is the ultimate promise of science fiction, and perhaps the ultimate violation of nature's finality. This is the theory of quantum archaeology, a fringe idea that suggests death may not be the permanent erasure we believe it to be. It proposes that if we could somehow obtain the complete quantum state of every particle in a given region of space at a specific moment in the past, we could, in principle, reconstruct anything that ever existed: a lost work of art, a vanished city, or a person who died 1,000 years ago. This is not time travel, but a form of cosmic resurrection through information. The logic stems from a core principle of quantum mechanics. In theory, the universe is deterministic at the quantum level. If you knew the precise position, momentum, spin, and all other properties of every fundamental particle in a system, and you knew all the forces acting upon them, you could, using the laws of physics, calculate their entire past and future. This is the dream of Laplace's demon applied to the subatomic world. Quantum archaeology takes this a step further. It argues that the information that constituted a person, the specific arrangement of atoms that made up their body, their brain, and crucially, the neural patterns that held their memories and personality, is not truly destroyed at death. That information simply dissipates, scattering into the environment as the body decomposes, and its particles are recycled into the earth, the air, and other living things. The data is scrambled, but according to quantum theory, it is never truly lost. Therefore, the staggering task of resurrection becomes one of information recovery and reconstruction. Imagine a future civilization with technology beyond our comprehension. They would need a device of unimaginable power, a quantum scanner of sorts, capable of reading the present state of the entire universe. From this snapshot, they would then run a cosmic-scale simulation backward in time, tracing the paths of every particle through history, filtering out the noise, and isolating the precise configuration that once was, say, Leonardo da Vinci in his studio in 1503. Once that exact quantum blueprint is identified, they could then use advanced matter manipulation, perhaps nanotechnology or something like a replicator, to reassemble those particles into the exact same configuration, atom for atom, electron for electron. In that moment, Leonardo da Vinci would stand before them, not a clone, but a perfect resurrection with all his memories intact, thinking his last thought from the instant before his original death. The philosophical hurdles are immediate and profound. Is this resurrected individual truly the same person, or just an identical copy with the same memories? From a materialist perspective, if every particle is identical, then yes, it is the same. Consciousness would presumably arise from that specific arrangement, just as it did the first time. But this leads to a disturbing question of identity. What if the original information was not completely lost? What if the original particles that made up that person are still out there, now part of a tree or a cloud? Would there now be two legitimate claims to that one identity? the theory also assumes consciousness is purely a product of physical arrangement with no extra physical soul or essence. If it is, then quantum resurrection is a logical, if distant, possibility. If it is not, then you would create a perfect biological shell, but an empty one. The practical obstacles, however, are so immense they border on the absurd. The computational power required to model every particle in a planet, let alone a universe across millennia, is incalculable. It would require understanding and simulating every quantum interaction across all of time, a feat that makes even building a Dyson sphere around a star seem trivial. Any error, no matter how minute, in tracking a single particle's history over centuries would cascade through the simulation, rendering the reconstruction flawed. Furthermore, the Heisenberg uncertainty principle itself states we cannot know both the exact position and momentum of a particle simultaneously. This fundamental limit of quantum mechanics suggests the perfect knowledge required for a flawless reconstruction is physically impossible to obtain. We could only ever create an approximation, a being very, very close to the original, but perhaps not the original in the strictest sense. Yet the idea persists not as a practical blueprint, but as a philosophical lightning rod. It forces us to confront what we mean by identity, memory, and the self. It challenges the finality of history, suggesting that no event is ever truly lost, only waiting to be decoded from the faint quantum echoes that still reverberate through the present. In a universe where information is eternal, our lives may not be fleeting stories but permanent inscriptions in the cosmic ledger, waiting for a reader with the right key. The holographic universe is a beautiful mathematical idea, but does it leave any fingerprints we can actually see? Physicists are not content with theory alone. They are hunting for observational evidence, subtle signatures that our three-dimensional reality is a projection from a two-dimensional surface. One of the most promising places to look is not out at the vast cosmos, but inward at the most destructive objects we know, black holes. The holographic principle was born from the black hole information paradox, and it is there that it makes a startling prediction. The principle states that the maximum amount of information or entropy any region of space can contain is proportional to its surface area, not its volume. For a black hole, this means all the data about every star, planet, or spaceship that ever fell in is not lost inside the singularity, but is encoded on the event horizon, the black hole's two-dimensional boundary. This is like saying the entire contents of a library are not stored on the shelves in the building, but are etched onto the surface of its outer walls. If this is true for black holes, the ultimate prisons of information, then why not for the universe as a whole? Our entire cosmos could be a black hole's interior scaled up to an unimaginable degree, with the cosmic horizon at the edge of the observable universe acting as the giant screen where all information is stored. This radical scaling suggests a testable limit. If we calculate the information content of any patch of space based on its volume using standard quantum theory, we should get one answer. But if the holographic principle is correct, the actual information capacity should be vastly smaller, constrained by the area surrounding that patch. Researchers are looking for places where our standard volumetric calculations of information break down, as these could be the points where the holographic nature of reality is forced to reveal itself. Another frontier in this search is the cosmic microwave background, the universe's oldest light. This afterglow is not perfectly smooth. It contains tiny temperature fluctuations, hot and cold spots that are the seeds of all future galaxies. These fluctuations are like the pixels on the cosmic projector screen. If our three-dimensional universe is a holographic projection, then the patterns in this background radiation should contain hidden correlations, a specific kind of noise or statistical signature that can only come from information originally encoded on a two-dimensional surface. Some teams have analyzed the data from satellites like Planck and claim to find hints of these exact anomalies, patterns that align more with a holographic universe than with standard inflationary models. These potential signals are incredibly faint and hotly debated, but the search is active and profound. It means scientists are treating the cosmos like a hard drive, scanning its oldest data for compression artifacts, for traces that the image we see is rendered from a simpler, flatter source code. The implications of finding such evidence would be a revolution on par with Copernicus or Einstein. It would mean that the depth we experience, the space between stars, the distance to a loved one, is an emergent illusion, a magnificent side effect of information processing on a distant, flat boundary we can never touch. Your entire life, with all its richness and dimension, would be a story written on the surface of a sphere at the end of the universe, played back to you in breathtaking, convincing 3D. The quest to prove we live in a hologram is not about diminishing reality, but about uncovering its deepest, most elegant structure, where the universe's truest self is a kind of sublime cosmic graffiti. A hologram's pixels are subtle, but a simulation might crash. If our reality is a digital construct, then even the most flawless code could contain bugs, tiny imperfections, or arbitrary limits that betray its programmed nature. These are the proposed glitches in the matrix, anomalies in physics that some scientists and philosophers suggest could be evidence we live in a simulation. One of the most compelling places to look is at the very extremes of energy. When ultra-high energy cosmic rays, particles from deep space traveling at nearly the speed of light, smash into Earth's atmosphere, they create a shower of secondary particles. Our models predict these cosmic rays can come from anywhere in the sky. Yet, intriguingly, some of the most energetic ones ever detected appear to arrive from directions that are suspiciously empty of known cosmic accelerators, like active galaxies. This could be a simple gap in our knowledge, or it could be something else. If the universe is a simulation, rendering every detail with perfect fidelity across vast distances requires immense processing power. To save resources, the simulation might simplify distant, unobserved regions, only rendering them in high detail when someone or something looks. A cosmic ray from such a region might carry the signature of that simplification, an energy or trajectory that seems slightly off because it originated from a lower resolution part of the code. Another potential glitch lies in the bizarre heart of quantum mechanics. The double-slit experiment is a cornerstone of quantum weirdness, where a single particle seems to pass through two slits at once, interfering with itself like a wave. This behavior only happens when we are not watching which slit it goes through. The moment we place a detector to observe the path, the particle behaves like a single, solid object. This collapse of the wave function is standard physics, but its implications are odd. In a simulation, this makes perfect sense as an optimization. Why waste processing power calculating all possible paths for a particle if no one is checking? The simulation only calculates the definite path when an observation is made, just as a video game only renders the graphics on the part of the map your character can see. The very act of observation could be the trigger that forces the simulation to commit to a single, rendered outcome. Then there are the mathematical constants themselves. The fundamental numbers that govern our universe, like the strength of gravity or the mass of an electron, appear to be exquisitely fine-tuned for the existence of complex life. If the force of gravity were slightly stronger, stars would burn out too quickly. If slightly weaker, they might never form at all. This fine-tuning has long puzzled scientists, leading to the anthropic principle, which states we observe these values because they are the only ones that allow us to exist. But from a simulation perspective, this fine-tuning could have a different explanation. It looks like the parameters were deliberately set. A programmer or many programmers running ancestor simulations might adjust these constants to see what kinds of universes and life emerge. Our particular set of numbers might not be a lucky accident, but a chosen configuration, one of countless simulation runs with different physical laws. We exist in this one because it produced observers who could ask the question. Even the structure of reality at the smallest scales might hint at a digital foundation. Some interpretations of quantum mechanics suggest space-time itself might be discrete, composed of tiny, indivisible units like pixels on a screen or bits in a computer. This idea of a fundamental Planck length below which distance becomes meaningless aligns eerily well with the concept of a simulation running on a finite grid. There would be a maximum resolution to reality, a pixel size for the cosmos. While we have no direct evidence for this yet, the search continues in experiments probing the fabric of spacetime. The goal is not to find a floating green line of code in the sky, but to uncover limits or patterns in nature that seem arbitrary from a physical standpoint, yet perfectly logical from a computational one. A simulation would have to have rules to prevent it from crashing, constraints on what can be calculated. Finding such a constraint, a cosmic speed limit or an energy ceiling that makes no physical sense other than to preserve system stability, would be the closest thing to a developer's signature. We are left testing the edges of reality, not just to understand the universe, but to see if it ever returns an error message. The quantum suicide experiment takes the cold logic of many worlds and makes it terrifyingly personal. It is not a test you would ever want to run, but as a thought experiment, it pushes the implications of infinite branching to a shocking extreme. Imagine a device is built, a gun perhaps aimed at a volunteer. This gun is not triggered by a person, but by a quantum random number generator, something that measures the spin of an electron. If the result is spin up, the gun fires. If it is spin down, it does nothing. The odds are exactly 50-50. From an outside observer's perspective, this is a grim game of chance. They would see the volunteer pull the trigger, hear either a bang or a click, and witness one clear outcome. They might see the person die or see them survive. In their branch of reality, the story ends there, but from the volunteer's own first-person point of view, what happens? According to the strict many worlds interpretation, every quantum event causes the universe to split, so when the trigger is pulled, reality divides. In one branch, the electron is spin up, the gun fires, and the volunteer dies instantly. In the other, equally real branch, the electron is spin down and the volunteer lives. Now, here is the unsettling crux of the argument. The volunteer's conscious experience can only continue in branches where they are alive. They cannot subjectively experience being dead. Therefore, from their own perspective, no matter how many times they pull the trigger, they will only ever hear a click. They will always find themselves in the branch where the quantum dice rolled in their favor. To an outside observer, the volunteer might appear impossibly lucky, surviving a 50-50 chance a dozen times in a row. But from the volunteer's vantage point, there is no luck involved, only the inevitable flow of their consciousness along the single thread of reality in which they continue to exist. This experiment scales to every moment of your life, every near miss, every accident avoided, every time you survive a risky situation. There are branches where you did not. The version of you listening right now is by definition the one that has survived every single quantum lottery up to this point. You are the cat that always finds itself alive when the box is opened. This leads to a bizarre and isolating form of immortality. As you age, you would find yourself surviving increasingly improbable events. A version of you might live through a plane crash that kills everyone else, then a building collapse, then a catastrophic illness, always the sole survivor through what looks like a series of miracles. You would become a statistical anomaly, watching everyone around you eventually perish in your branching timelines, while your own consciousness persists, forever following the path of survival. The theory forces a brutal confrontation with identity. Are you the same continuous self, or are you a new, nearly identical copy spawned at each branching point, inheriting the memories of a version that just died in another world? The you that survives the car crash is not the you that perished, but a separate entity in a separate universe who believes with absolute conviction that they are the original. This challenges our deepest intuition about being a single, unified person. Philosophically, quantum suicide is less a recipe for immortality and more a stark spotlight on the chasm between objective reality and subjective experience. It highlights that in a multiverse where all possibilities are real, your conscious awareness is locked onto a single, survivable thread, a path through the infinite forest where you never, ever encounter your own end. The silence of your own death is a silence you are logically destined never to hear. The pull of the dark flow is not the only current in our cosmic sea. Closer to home, our entire galaxy and its neighbors are caught in a powerful, mysterious river, all streaming toward a specific point in space with immense gravitational hunger. Astronomers call this point the Great Attractor. It lies in the direction of the constellation Centaurus, hidden behind the dense stars and dust of our own Milky Way's galactic plane, a cosmic siren we cannot directly see. This region has the gravitational pull of tens of thousands of galaxies, a mass so colossal it is drawing our local group of galaxies, including Andromeda and our own Milky Way, toward it at a staggering speed of over 1 million miles per hour. For decades, its nature was a profound puzzle. What could be massive enough to command such motion? The initial fear was that it was a massive, unseen concentration of matter, a hypercluster of galaxies which would challenge our models of cosmic structure. But as our observational tools, like X-ray telescopes that can peer through galactic dust, improved, the picture grew even larger and more strange. We discovered that the Great Attractor itself is not the final destination. It is merely a waypoint. Our entire galactic river, including the Great Attractor region, is being pulled towards something even more immense and distant, a structure so vast it defies easy comprehension. This is the Shapley supercluster, a titanic collection of over 8,000 galaxies, one of the largest known structures in the observable universe. It acts as a gravitational anchor on a scale we are only beginning to map. Yet, the story of cosmic motion requires both a pull and a push. For every great attractor, there must be a corresponding void, an emptiness whose lack of gravity creates a repulsive effect. This is where the dipole repeller enters the narrative. While we are being pulled toward the Shapley supercluster, we are also being pushed from behind by a colossal cosmic emptiness. The dipole repeller is an enormous region of exceptionally low density, a void so vast and empty that its gravitational influence is effectively negative. Imagine sitting in a boat on a calm lake. If you are near a powerful drain, you will be pulled toward it. But if you are also in a current created by water flowing away from a massive, empty basin behind you, you will be pushed as well. The dipole repeller is that basin. Its lack of matter means there is less gravitational pull holding us back, so the stronger pull from the Shapley supercluster wins out, accelerating our journey. We are in a cosmic tug of war between an unfathomable concentration of mass and an equally unfathomable absence of it. This grand dance of push and pull reveals a universe structured on scales that humble the imagination. We are not floating in a random, expanding void. We are part of a dynamic web where galaxies flow along gravitational watersheds, pulled towards superclusters and pushed from voids in a slow, relentless current. The dark flow hinted at something beyond our horizon, but the Great Attractor and the dipole repeller show that even within our observable universe, our place is not passive. We are on a journey swept along by architectures of matter and emptiness so large they curve the very path of our galaxy through the cosmos. It forces a question about what other invisible geographies, what other attractors and repellers are shaping the grand flows we have only just begun to trace. The concept of life drifting between the stars found its most tantalizing and contentious real-world test case in October 2017. That is when astronomers at the Pan-STARRS telescope in Hawaii spotted an object unlike any seen before. It was tumbling through our solar system at high speed, and its trajectory was unmistakable. It was not orbiting our sun, it had come from interstellar space. They named it Oumuamua, Hawaiian for scout or messenger from afar. This was the first confirmed visitor from another star system, and from the moment of its discovery, it defied easy explanation. Its observed properties were deeply strange. First, its shape. Based on how its brightness changed dramatically as it rotated, scientists inferred it was highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a flattened pancake. No known natural asteroid or comet from our own solar system has such an extreme shape. Second, and more puzzling, was its motion. As Oumuamua sped away from the sun, it accelerated slightly as if being pushed. Comets do this when their icy surfaces heat up and vent gas, creating a natural rocket effect. But Oumuamua showed no visible coma, no cloud of gas and dust, no tail. It was dark and inert. If it was outgassing, it was doing so invisibly, which would be bizarre for a simple iceberg from another star. This is where Harvard astronomer Avi Loeb entered the fray with a provocative hypothesis. He suggested we should consider the possibility, however slim, that Oumuamua was not a natural object, but a piece of advanced technology. Specifically, Loeb and his colleague calculated that the observed non-gravitational acceleration could be perfectly explained if Oumuamua was a very thin, lightweight object pushed by the pressure of sunlight itself, a light sail. A light sail is a proposed spacecraft design that uses the tiny but constant pressure of photons from a star to accelerate, needing no fuel. If Oumuamua was a discarded light sail, perhaps broken off from a larger vessel, its unusual shape and motion would make sudden, coherent sense. Its tumbling could be the result of a collision or malfunction, and its lack of outgassing or a dust tail is exactly what you would expect from a solid, manufactured object. Loeb argued that the simplest explanation was not necessarily a natural one we had never seen before, but a technological one that fits the data without requiring new physics. He framed it as a question of scientific openness. When we encounter something anomalous, should we not at least consider all possibilities, including an artificial origin? The mainstream astronomy community largely pushed back, proposing natural explanations. Some suggested Oumuamua could be a fractal-like dust aggregate, a hydrogen iceberg, or a nitrogen iceberg chipped off a Pluto-like exoplanet. These ideas, while creative, often required exotic materials or conditions not observed in our own solar system. The debate highlighted a fundamental shift in our relationship with the cosmos. For the first time, we had an object from another star in our backyard, and we lacked the tools and the time to study it properly. Oumuamua is now far beyond the reach of our telescopes, a silent enigma receding into the dark. But it will not be the last. More interstellar visitors have since been detected, like the comet Borisov, which behaved much more predictably. The key lesson from Oumuamua is that we must be ready for the next one. This is where the theory of directed panspermia meets modern astronomy. If an advanced civilization wished to seed life across the galaxy, they would not send fragile, living organisms on a million-year journey through the harsh radiation of space. They would send the blueprint, they would encode the genetic instructions for life, or even for a self-replicating constructor, into a durable, information-dense medium. This could be embedded in a small, rugged probe, perhaps disguised as a natural asteroid, and accelerated across interstellar space by a powerful laser or a light sail. When such a probe reached a promising star system with watery worlds, it could activate using local resources to build a facility that synthesizes the encoded life forms and begins the seeding process. Oumuamua, in this speculative framework, could have been a scout, a piece of such a vessel, or even a derelict seed pod itself. To test this for future visitors, our approach must be multifaceted. First, we need early warning systems to detect these objects as they enter the solar system, giving us time to mount an interception mission. a spacecraft could rendezvous with the object, photograph it in detail, and even land on it. We would look for unambiguous signs of engineering like right angles, metallic surfaces, welded seams, or isotopic ratios in its material that suggest artificial refinement. We could scan for electromagnetic emissions or internal structures. Even more subtly, we could search for information content. If directed panspermia is the goal, the object might contain a message not in radio waves, but in its very atomic arrangement, perhaps in the ordered sequences of minerals or in patterns within any ice it carries, a biological or technological primer waiting for the right conditions to be read. The legacy of Oumuamua is not a conclusion but a catalyst. It has forced us to draft the playbook for investigating interstellar objects with the seriousness they deserve. It reminds us that the boundary between natural and artificial may be the most important frontier we ever explore. The next strange rock from a distant sun might be just a rock. Or it might be the first page of a manual written by a civilization that decided the best way to spread life was to mail it, postage due, across the galaxy. The paradox of lost information is a crisis that demands a revolution. Two of the most profound solutions to the black hole information paradox do not just rescue information, they radically redefine the nature of reality itself, suggesting that space, time, and entanglement are all facets of a single, deeper truth. The first solution returns us to the holographic principle. We previously explored it as a grand cosmic idea, but its most precise application is right at the edge of a black hole. This solution states that when matter falls in, its information is not lost inside. Instead, it is scrambled and imprinted onto the two-dimensional surface of the event horizon, like data being burned onto a DVD. The three-dimensional interior we imagine is just a projection of that data. As the black hole evaporates via Hawking radiation, this information on the surface is slowly, chaotically released back into the universe, encoded in the correlations between the emitted particles. It is not a clean retrieval, but the information is in principle preserved. The universe does not forget. This idea transforms the black hole from a cosmic shredder into the ultimate hard drive, with its event horizon as the platter where all data is stored. The second solution is even more geometrically beautiful and bizarre. It is called ER equals EPR. This is not a slogan, but a profound equation proposed by physicists Juan Maldaisner and Leonard Susskind. It proposes a direct link between two concepts that seemed utterly separate. ER stands for Einstein-Rosen bridges, the formal name for wormholes, tunnels through spacetime. EPR stands for Einstein-Podolsky-Rosen, the trio who first highlighted the strange phenomenon of quantum entanglement, that spooky connection between particles. The equation boldly states they are the same thing. In this view, when two particles become quantumly entangled, they are not communicating faster than light through empty space. They are, in fact, connected by a microscopic wormhole, a bridge in the geometry of spacetime itself. Entanglement is not a force, it is architecture. Apply this to a black hole and the information paradox begins to untangle. Imagine a pair of entangled particles. One falls into the black hole while its partner escapes as Hawking radiation. According to ER equals EPR, these two particles are not separate entities sending mysterious signals. They are connected by a tiny wormhole. This wormhole is the thread that preserves the information. The particle inside and the particle outside are still one connected system, ensuring the information about what fell in is never truly severed from the outside universe. It is always there, woven into the fabric of space-time, connecting the interior to the exterior. This suggests a staggering possibility. The interior of a black hole might not be a place you can ever visit, but it is not a disconnected prison either. It is eternally linked to the outside via a labyrinth of these quantum wormholes, a hidden geometry that upholds the laws of quantum mechanics. The evaporation of a black hole would then be the gradual transfer of this complex, wormhole-braided structure to the outgoing radiation. The information was never in the hole, it was in the connections. These two solutions, holography and ER equals EPR, are not necessarily competing. They may be two different descriptions of the same underlying reality. The hologram could be the way the information appears to us, while the wormholes describe the actual geometric substrate that makes the hologram possible. Together, they paint a picture where the distinction between information and space-time blurs. The universe is not a container with things in it. It is a network of relationships where what we call space is born from a vast web of quantum connections. The black hole, the ultimate paradox, becomes the key that forces us to see this deeper layer, where every bit of information is a stitch in the fabric of reality. The Sun's surface is a seething ocean of plasma, but its outer atmosphere, the corona, presents one of the most enduring mysteries in all of solar science. This wispy, tenuous halo of gas is not cooler than the surface, as you would expect when moving away from a fire. It is scorchingly hot, blazing at millions of degrees, while the visible surface below simmers at a mere 10,000. Mainstream solar physics explains this through the intricate dance of magnetic fields. The Sun's churning interior twists and braids these fields into complex shapes. When these magnetic lines snap and reconnect, they release titanic bursts of energy that violently heat the corona like a rubber band stretched until it breaks. This process also drives solar flares, those sudden, brilliant eruptions and coronal mass ejections, the billion-ton clouds of plasma hurled into space. It is a model of magnetic dynamism where the Sun is a giant, self-contained magnetic engine. The electric universe theory offers a radically different source of power. It proposes the Sun is not an isolated nuclear fusion reactor, but a charged object in a galactic circuit. In this view, the Sun acts as a focus or anode for electrical currents flowing through the plasma of interstellar space. The incredible heat of the corona is not generated internally by magnetic reconnection, but externally by electrical energy delivered to the Sun's surface. Imagine the Sun as a giant, luminous electric light bulb. The bright photosphere is the filament, and the corona is the glowing halo of plasma around it, energized by the current flowing through it. This electrical input, proponents argue, is what truly heats the corona to such impossible temperatures. This perspective also reframes solar flares and prominences. In the Standard Model, a flare is a catastrophic release of magnetic energy. In the electric universe, it is a stellar-scale electrical discharge, a cosmic lightning bolt erupting from the Sun's surface as it equalizes a charge imbalance with its surrounding plasma environment. The vast, looping prominences that arc hundreds of thousands of miles above the surface are not held aloft by magnetic tubes alone, but are seen as examples of plasma filaments, shaped and powered by the same electromagnetic forces that create intricate glowing beams in laboratory plasma balls. The theory extends this electrical reasoning to explain planetary auroras, the shimmering curtains of light at Earth's poles. Standard science describes them beautifully. Charged particles from the solar wind are captured by Earth's magnetic field and funneled toward the poles where they collide with atmospheric gases, causing them to glow. The electric universe agrees on the glow but disagrees on the source of the power. It suggests the aurora is not primarily powered by particles from the solar wind, but by direct electrical currents flowing between Earth and the Sun, part of that same galactic circuit. Earth, in this model, is not a passive recipient of solar wind, but an active component in a solar system-wide electrical network. The glowing auroral oval is the visible sign of this circuit closing, where electricity discharges into our upper atmosphere, much like a neon sign lighting up. This electrical framework makes a bold claim about prediction. Proponents argue that if solar activity is driven by external electrical inputs from the galaxy, then the sun's behavior might be influenced by its position within the Milky Way's hypothesized electrical currents or by the arrival of charged interstellar material. This could potentially link solar cycles and periods of intense activity to larger cosmic patterns, something traditional magnetic models focused on internal dynamics do not account for. While mainstream astrophysics finds the evidence for magnetic reconnection overwhelming and sees no need for external electrical power sources, the electric universe challenge persists. It asks us to see connections where we see separation, and to consider whether the sun's fiery temper is its own or a reflection of a galaxy alive with invisible currents. Archaeology holds a ledger written not in ink but in ice and wood. To test the phantom time hypothesis, we must look beyond European chronicles to records kept by nature itself, and by civilizations far from the influence of any alleged medieval conspiracy. Dendrochronology, the science of tree ring dating, builds an unbroken timeline stretching back thousands of years. By matching the pattern of wide and narrow rings from living trees to ancient timbers in buildings and bogs, scientists have constructed a continuous sequence that covers the exact centuries Herbert Illig claims never happened. Oak trees from Ireland and Germany show clear annual growth rings for every single year between 614 and 911. These trees were not reading fabricated papal decrees. They were responding to the real, seasonal climate of those years, a climate that left its fingerprint in the cellulose. There is no gap in the wood. Even more definitive are the ice cores drilled from the ancient glaciers of Greenland and Antarctica. Each year's snowfall compresses into a layer, trapping bubbles of the atmosphere and dust from volcanic eruptions. These layers form a pristine, year-by-year archive of Earth's climate. Cores like the Greenland Ice Sheet Project 2 show an unambiguous, continuous sequence of annual layers right through the Phantom period. Crucially, they record known volcanic events from other cultures' histories. A massive, global volcanic signature dated to around 536, linked to extreme cooling and crop failures worldwide, appears exactly where it should in the core, centuries before the alleged phantom time began. This global event, witnessed and recorded by cultures from Byzantium to China, anchors the timeline in geology, not politics. The astronomical evidence from outside Europe is perhaps the most damning. Chinese imperial astronomers kept meticulous, date-stamped records of celestial events for dynastic purposes. Their archives detail observations of solar eclipses, comets, and planetary conjunctions that occurred during the supposed phantom centuries. For instance, they recorded a total solar eclipse on July 3, 761. Using modern astronomical software to run the clock backwards, we can confirm that a total eclipse was indeed visible in China on that exact date. The Chinese did not base their calendars on the whims of a Holy Roman Emperor. They based them on the immutable motion of the heavens. Their independently verified observations create a lockstep chronology with the rest of the world. Furthermore, the sheer global interconnectedness of the timeline makes a conspiracy impossible. While Illig focused on a gap in Western European records, the seamless flow of history elsewhere is overwhelming. In Central America, the Maya long count calendar progressed without interruption, their detailed inscriptions chronicling kings and wars right through the 8th and 9th centuries. In the Middle East, the rise of Islam, the founding of Baghdad in 762, and the golden age of the Abbasid Caliphate all occupy this period, documented in vast libraries of Arabic texts. In Japan, the Nara period saw the construction of the Great Buddha and the flourishing of a documented court culture. These civilizations were not coordinating a lie with a German emperor and a pope. They were simply living their history, and their histories interlock like pieces of a planetary puzzle. The phantom time hypothesis ultimately fails not because it is uninteresting, but because it is too local. It attempts to solve perceived inconsistencies in one region by erasing 3 centuries of global human experience, from the ice sheets of Greenland to the observatories of Chang'an. The world's memory is stored in too many places, written in too many languages, and etched into the very planet itself for any single conspiracy to ever rewrite it. The past may be a story, but it is a story written in stone, ice, and starlight, and those pages cannot be torn out. The silence of the zoo is a policy of non-interference, a gentle quarantine. But what if the keepers are not benevolent curators but vigilant exterminators? This darker answer to the great silence is known as the Sentinel hypothesis. It proposes that the galaxy is not a quiet forest or a peaceful zoo, but a guarded orchard, and we have not yet drawn the attention of the gardener's shears. In this chilling scenario, an ancient, vastly powerful intelligence, or perhaps a network of automated probes, maintains a cosmic order. Their prime directive is not observation but sterilization. They silently monitor the galaxy for signs of dangerous technological activity, and when a civilization reaches a certain threshold, a point where it becomes too noisy, too expansionist, or too self-destructive, they eliminate it. This, the theory suggests, could be the true nature of the Great Filter. It is not an inevitable stage of development, but an imposed one. The filter is not behind us, and it is not a test we must pass. It is a wall we must avoid hitting, a silent alarm we must not trigger. The Sentinels would not necessarily destroy with brute force. Their methods would be efficient, undetectable, and total. A highly advanced civilization could deploy a tailored virus that rewrites a planet's biology, a nanite swarm that disassembles technology at the molecular level, or a gravitational tweak that gently nudges a deadly asteroid onto a collision course. The result is always the same, a return to quiet. The planet is reset, its technological civilization pruned away, leaving behind perhaps a scarred biosphere to begin the evolutionary experiment anew millions of years later. This explains the Fermi paradox with brutal elegance. The galaxy is not empty of life, it is littered with its graves. Every world that ever shouted into the cosmic dark with radio signals, or launched probes, or exhibited signs of harnessing stellar energy was quietly, permanently silenced. We do not see them because the Sentinels are very good at their job. The great silence is not a sign of absence but of cleanliness. Our own survival thus far could be read in two terrifying ways. Perhaps we are simply too primitive, too quiet to have registered on their sensors. Our radio and television broadcasts are barely a century old, a faint whisper just beginning to ripple outward. We are an anthill at the edge of a highway, not yet noticed by the passing traffic. Or more ominously, perhaps we have already been noticed and we are currently being assessed. Every nuclear test, every climate shift from industrial activity, every leak of synthetic biology into the environment could be a data point in a silent evaluation. Are we a nurturing species or a cancerous one? Do we create beauty and seek knowledge, or do we only consume and destroy? Our fate may hang on an interpretation of signals we do not even know we are sending. This transforms our search for extraterrestrial intelligence from a hopeful scan for friends into a perilous game of hide and seek where being found could mean the end. It suggests that the pinnacle of cosmic wisdom is not expansion but subtlety. The oldest, wisest civilizations in the galaxy might not be the ones broadcasting their presence, but the ones who learned long ago how to disappear completely, to live in harmony with their world and never, ever attract the gaze of the silent gardeners. Our dreams of colonizing the stars might be the very dreams that condemn us. The Sentinel hypothesis offers no comfort, only a profound and unsettling caution. The universe may not be a dark forest where every hunter hides. It may be a carefully tended garden, and we are a new, wild shoot. The question is not whether we will be discovered, but what the gardener will do when he decides we are a weed. Anesthesia presents a profound and practical mystery for any theory of the mind. How can a few specific molecules, inhaled or injected, completely erase the inner universe of consciousness while leaving the brain's basic electrical activity and life support systems running? For the standard classical model of the brain, this is a complex pharmacological puzzle. For the quantum consciousness theory, it could be a critical test, a potential key to unlocking the mechanism of awareness itself. Proponents of the Orch-or model, like anesthesiologist Stuart Hameroff, argue that anesthetics do not just dampen neural firing, they may specifically target the delicate quantum processes they believe underlie consciousness. The clue lies in a curious and consistent property of anesthetic gases. Their potency is directly correlated with their ability to dissolve in a non-polar medium, like the oily interior of a cell membrane. This suggests they are acting not on proteins or receptors in the synaptic gaps, as many drugs do, but within the lipid layers of the neurons themselves. This is exactly where the microtubules, the proposed quantum computers of the brain, are located. Hameroff and others hypothesize that anesthetic molecules nestle into these lipid regions, disrupting the quantum coherence within the microtubules. They essentially act as quantum decoherers. In the warm, wet brain, maintaining quantum superposition is a fragile balancing act. Anesthetics, according to this view, tip the scales. They introduce enough environmental noise to prevent the microtubules from sustaining the large-scale quantum coherence necessary for objective reduction, the moment of proto-consciousness. The brain's classical functions continue, the patient is alive, and their brain may even show organized electrical waves, but the orchestrated quantum collapses that give rise to subjective experience are silenced. It is like scrambling the signal in a radio receiver. The hardware is intact, but no music plays. This idea leads to a bold and testable prediction. If quantum processes in microtubules are the seat of consciousness, then substances that do not follow this lipid solubility rule should not affect awareness, even if they mimic other effects of anesthesia. Intriguingly, there are such substances. Certain inert gases like xenon are excellent anesthetics. Others, like helium, are not, despite having very similar physical properties. The difference may lie in their electron configurations and how they interact with these proposed quantum sites. Researchers are now designing experiments to probe this directly. One approach uses advanced spectroscopy to look for signs of quantum vibrations in microtubules and to see if anesthetics suppress those vibrations at the same concentrations that erase consciousness in animals. Another looks for subtle quantum effects in much simpler systems, like single-celled organisms that lack a nervous system but still exhibit primitive decision-making and contain microtubules. If anesthetics disrupt similar behaviors in these organisms, it would suggest they are acting on a fundamental, pre-neural biological process that could be quantum in nature. Of course, mainstream neuroscience remains deeply skeptical. Critics argue that the effects of anesthetics are well explained by their action on known neural receptors, like GABA receptors, which slow down overall brain communication. They see the quantum explanation as an unnecessary complication, adding a layer of mystery where established biology suffices. The burden of proof lies with the quantum consciousness theorists to show that anesthetics do something more specific than just generally depressing neural activity. Yet the very existence of anesthesia, this magical switch for the self, challenges our understanding. It demonstrates that consciousness is not an all-or-nothing product of a brain being on. It is a specific, chemically vulnerable state. Whether the key to that switch is found in the classical firing of neurons or in the silent, quantum hum inside them remains one of the most intimate and urgent frontiers of science. The answer may not just tell us how we go to sleep under the surgeon's hand, but what it truly means to be awake in the first place. That colossal chill on the cosmic map, the cold spot, is more than a statistical fluke. It is a billion light-year-wide bruise on the infant universe, a region so profoundly cold that the simplest explanation, a giant void, seems insufficient. This has led cosmologists to a breathtaking alternative, one that reaches beyond our universe entirely. The cold spot might be a cosmic scar, the lingering imprint of a violent collision with another universe during the first moments of creation. To understand this, we must revisit cosmic inflation, that period of unimaginably rapid expansion just after the Big Bang. The leading theory suggests our entire observable universe inflated from a tiny quantum seed stretching spacetime faster than light. But what if ours was not the only seed? In the multiverse model known as eternal inflation, the greater cosmos is a frothing, bubbling sea of false vacuum energy. In this sea, random quantum fluctuations can trigger new inflationary bubbles, each one a new universe with its own laws of physics, budding off endlessly. These bubble universes are not floating in empty space as we know it, but in the inflating background medium, a higher dimensional landscape. As these bubbles expand, they can sometimes collide. Picture two soap bubbles gently touching and merging in a sink. Now scale that up to a cosmic cataclysm. If another bubble universe collided with ours during its own inflationary infancy, the impact would have transferred immense energy at the point of contact. For our newborn universe, this would have been like a sledgehammer blow to the fabric of spacetime. The collision would have drained energy from that region of our cosmos. In the frantic aftermath, as our universe continued to inflate and then cool, that traumatized patch would have been left with less thermal energy than its surroundings. Billions of years later, when the cosmic microwave background radiation finally broke free, that region would shine colder, a permanent shadow on the sky marking the point of impact. The cold spot in this view is not an empty void but a fossilized dent, a relic of a time when our universe was not alone. It is the first potential observational evidence that we live in a multiverse, a single bubble that once brushed against a neighbor. The implications are staggering. If this theory is correct, then the cold spot is a window not just into the early universe but out of it. It suggests that the greater reality is a teeming metropolis of universes, most forever separate but occasionally close enough to touch. That faint, cold patch on the map of creation could be our only clue that our entire cosmic story is just one volume in an infinite library. Beneath the moon's tranquil seas of hardened lava, something massive and unexpected lurks. These are the mascons, short for mass concentrations, and they are one of the moon's most peculiar geological features. When the Apollo missions orbited the moon, scientists noticed something strange. The spacecraft would speed up slightly, then slow down, as if being tugged by hidden pockets of extra gravity. These gravitational anomalies were mapped to the large, circular basins we see as dark lunar seas or Maria. It turned out that beneath these flat plains, the moon's mantle is denser and heavier than elsewhere. The leading scientific explanation is compelling. Billions of years ago, colossal asteroids slammed into the moon, creating giant impact basins. Later, the moon's interior was still hot, and vast floods of dense basaltic lava welled up from below, filling these basins and solidifying. This dense material, sitting in a concentrated pool, creates the extra gravitational pull, a massive plug of heavy rock in a crater-shaped mold. But to some, the mascons feel too perfectly placed, too coincidental. They are not randomly scattered, but centered precisely under these circular seas. Could this be a natural consequence of impact and volcanism, or might it hint at a deliberate structural reinforcement beneath what looks like a manufactured surface? The mascons act like gravitational anchors, subtly stabilizing the moon's rotation in a way that keeps one face forever turned toward Earth, a beneficial trait for any observation platform. This lopsidedness extends far beyond hidden masses. The moon itself is fundamentally asymmetric in a way that defies simple explanation. Its crust is dramatically different on the near side we see, compared to the far side hidden from view. The familiar near side is dominated by those dark, smooth maria, the great seas of frozen lava. The far side, however, is a rugged, battered highland, almost completely covered in craters and virtually devoid of the large, dark plains. It is as if the moon has two completely different faces. Even more telling, the crust on the far side is significantly thicker by tens of kilometers than the crust on the near side. This is not a minor variation, it is a fundamental structural imbalance. Why would a natural satellite formed from the debris of a giant impact or captured from deep space end up with such a pronounced and consistent dichotomy? Mainstream planetary science offers models involving the moon's cooling history and the gravitational pull of Earth, suggesting that the near side remained hotter longer, allowing more volcanic activity to resurface it, while the far side cooled and solidified into a thicker, older crust. Yet, the starkness of the divide remains puzzling. When you combine the mascons, those dense, gravity-anchoring plugs, with the moon's profound crustal asymmetry, a pattern of oddity emerges that fuels the most speculative interpretations. In the moon matrix theory, these are not random geological quirks, but design features. The mascons could be interpreted as structural ballast, carefully placed to maintain the moon's precise orientation and orbital stability, ensuring its one face remains a perpetual window to Earth. The thicker crust on the far side might then serve as a protective shield, armor plating against the constant bombardment of meteoroids from the depths of space, safeguarding whatever might lie within or on the opposite hemisphere. Together, they paint a picture of an object engineered for durability and purpose, with a reinforced back and a weighted, stable base. This is the kind of design logic you would apply to a spacecraft or a permanent installation, not a random ball of rock. While science diligently works to explain each piece with natural processes, the collective strangeness whispers a persistent question. Are we looking at a world shaped by blind chance and ancient violence, or at an artifact whose true blueprint is written in gravity and stone, a design we are only beginning to measure? The ultimate cosmic catastrophe would arrive without a whisper of warning. If a bubble of true vacuum spontaneously formed in some distant galaxy, its wall of rewritten physics would expand in all directions at the very speed of light. No signal, no flash of radiation, no gravitational wave could outpace it to herald its coming. The first and only sign of its arrival would be the transformation itself, a silent wavefront moving at the universal speed limit. From our perspective, the event would be instantaneous and total. One moment, our universe exists as we know it. The very next, a sphere of alien physics is already upon us, and then nothing we recognize as reality remains. This makes false vacuum decay perhaps the most existentially terrifying idea in all of physics, not just for its destructive potential, but for its absolute stealth. It is a perfect predator, moving at the maximum speed causality allows, leaving no time for reaction, no possibility of escape, and no legacy of our existence. This leads to a deeply unsettling thought experiment. Could it have already happened? Is the wavefront on its way right now, already having consumed galaxies millions of light years away, its silent approach hidden by the very fact that no information can precede it? We look at the distant cosmos and see galaxies shining, their light carrying stories from billions of years in the past, but that light is only a message from the past, not a live feed. A vacuum decay bubble that began 2 billion light years away 2 billion years ago would be arriving at Earth just as the light showing its point of origin, still undisturbed, finally reaches our telescopes. We could be watching the calm, serene image of a galaxy that has already been erased from existence, completely unaware that the wave of annihilation born there is crossing our threshold at this very second. This transforms the night sky from a window into the past into a potential gallery of ghosts, showing us a universe that may no longer exist. The theory, therefore, occupies a strange and frustrating place in science. It is rooted in solid quantum field theory and our best measurements of the Higgs field, yet it is arguably untestable in any practical sense. we cannot run an experiment to trigger it for obvious reasons. We cannot build a shield against it, as it would rewrite the rules that any shield is made from. We can only calculate probabilities, which currently suggest the metastable state of our vacuum is likely to last for timescales far, far longer than the current age of the universe. But probability is not a guarantee. In an infinite or near-infinite cosmos, even the most unlikely event will eventually occur somewhere. This imbues our existence with a profound and eerie fragility. Every second of continued reality is a silent victory against an unimaginable statistical improbability, a cosmic game of chance where we do not get to know if the dice have already been rolled against us. The false vacuum thus stands as the ultimate reminder that our understanding of reality is provisional. Our laws of physics, the constants we rely upon, the very space between atoms, could all be a local and temporary configuration, a calm eddy in a quantum field that is still searching for its true lowest state. We are living on borrowed time in a universe that might be, at its heart, asleep and dreaming, waiting for a random jolt to wake it into something else entirely. The silence of the cosmos might not be a graveyard, but a sign of a roadblock so immense it stops almost everyone before the journey truly begins. We have met the great filter, that daunting bottleneck in the evolution of intelligence. But if this filter is indeed behind us, making us miraculously rare, which specific step was the nearly impossible one? Was it the very spark of life itself, that first self-replicating molecule in a primordial sea? While profound, the rapid appearance of life on a young Earth suggests this step, while not easy, might not be the universe's ultimate showstopper. Perhaps the true filter is more subtle and far more cruel. It could be the leap from simple, single-celled prokaryotes to the complex, compartmentalized eukaryotic cell. For over 2 billion years, life on Earth was just bacteria and archaea, thriving but stuck in a microscopic world. Then, one day, through a fateful act of symbiosis or invasion, one cell swallowed another, and instead of destroying it, they forged an alliance. That captured cell became the mitochondria, the powerhouse of the new complex cell. This event was not a slow, evolutionary crawl, but a singular, freak accident of cellular cooperation that unlocked the potential for multicellular life, for plants, for animals, for us. This step appears to have happened exactly once in Earth's entire history. All complex life, from mushrooms to blue whales, descends from that one fragile merger. If such an event is astronomically unlikely on any world, then the galaxy could be teeming with bacterial slime, but forever silent of anything that could ever look up at the stars. The filter, in this case, is not death, but a stagnation that lasts for eternity. Another candidate lies not in biology, but in behavior. The development of persistent tool use and cumulative technology requires more than clever paws or beaks. It demands a specific cognitive cocktail, forward planning, social learning, and the ability to teach and build upon the discoveries of past generations. Many animals use tools, but their innovations are fleeting, lost when the individual dies. For a species to climb the technological ladder, it must escape this cycle. It needs language, culture, and a way to store knowledge outside the fragile biological memory of a single brain. Our own ancestors teetered on this edge for hundreds of thousands of years before something clicked and the pace of change exploded. That click, the transition from isolated cleverness to a collective, growing intelligence, might be a neurological fluke that most planets never witness. But the most haunting filter of all is the one we are staring down right now. It is the filter of self-annihilation through the very technology that promises a cosmic future. This is the filter that lies ahead. Every civilization, upon discovering the fundamental forces that bind matter, inevitably unlocks the power to unbind itself. Nuclear fission, biotechnology, artificial intelligence, climate manipulation, each is a double-edged sword of creation and destruction. the period between discovering such powers and achieving the wisdom to manage them without self-destructing might be vanishingly short. A civilization's technological adolescence could be its final act. In this view, the Great Silence is the echo of countless worlds that briefly flickered with radio signals, only to go permanently dark a century later. We are in that narrow window now, balancing on a knife's edge. Are we the exception, the first to navigate this minefield, or are we simply next in a long, silent line? The answer changes the meaning of everything we do. If the filter is behind us, we are precious and have a duty to spread. If it is ahead, our survival is the most important project in the universe. The digital age has transformed the Mandela effect from a personal oddity into a global phenomenon, a shared nervous system where one person's strange memory can become a community's verified truth. The internet is not merely a place where these false memories are reported. It is the very engine that amplifies, solidifies, and validates them. Before the web, someone misremembering the Monopoly man's monocle might have shrugged it off as a personal mistake, a quirky mental hiccup. Today, that same person can type, "Did the Monopoly man have a monocle?" into a search engine and instantly find thousands of others asking the same question, sharing their own vivid recollections and creating detailed compilations of evidence. This instant validation is powerful. It replaces individual doubt with collective certainty. The sheer number of people who share the memory becomes proof of its reality, overriding the contradictory evidence right in front of them. Online forums and social media groups become echo chambers, reinforcing the false memory through constant repetition and discussion. New members arrive, learn the correct false memory from the group, and often incorporate it into their own life stories, further expanding the community. The internet effectively curates and disseminates an alternative history, one that feels more real because it is shared by a tribe. This digital amplification taps into a deep human need to belong, to have our subjective experiences confirmed by others. When so many people remember the same specific detail incorrectly, it creates a powerful social bond, a sense of being part of a group that can see a hidden layer of reality. This makes letting go of the false memory emotionally difficult, as it would mean severing a connection to that community and admitting that one's own mind and the minds of thousands have been collectively fooled. So what is actually happening inside our brains to create this shared illusion? Psychology offers two key concepts that explain the Mandela effect far more simply than timeline shifts or simulation glitches: confabulation and the misinformation effect. Confabulation is not lying. It is the brain's innocent, automatic process of filling in gaps in our memory with plausible information. Our memories are not perfect video recordings. They are more like sketchy outlines, and when we recall an event, our brain reconstructs it, using logic, expectation, and general knowledge to color in the missing pieces. For example, the Fruit of the Loom logo features a pile of fruit. Our brains know that a classic visual symbol for abundance is a cornucopia, a horn of plenty. So when we vaguely remember a logo with fruit, our brain helpfully inserts the cornucopia because it fits the schema, the mental pattern for bounty of fruit. We are not remembering a different reality. We are remembering our brain's best guess, which has become fused with the original memory. The misinformation effect is the process where, after exposure to incorrect information, we incorporate that false detail into our memory of an event. This is where the internet's role becomes a perfect catalyst. Someone posts a compelling video titled, "Proof the Berenstain Bears were always spelled with an E." The video might show a digitally altered book cover or simply state the claim with authority. A viewer whose own memory of the book is fuzzy is now exposed to this strong, incorrect suggestion. Later, when trying to recall the spelling, their brain retrieves not the original, faint memory of the book, but the more recent, vivid memory of the compelling video. The misinformation has overwritten the original data. This effect is incredibly robust and is the basis for the unreliability of eyewitness testimony. Our memories are malleable, constantly being edited and rewritten, not by cosmic forces, but by our own psychology and the information we consume. The unique power of the Mandela effect lies in the collision of these two forces, the brain's innate confabulation and the internet's powerful misinformation network. A small, logical memory error, like assuming a famous line is "mirror, mirror" because it sounds more poetic, gets seeded online. It resonates with others whose brains made the same logical shortcut. They congregate, share their confabulated memories, which then act as misinformation for newcomers, creating a self-sustaining loop of false certainty. The community then goes looking for residue, for evidence in the real world that supports their memory. They find a bootleg T-shirt with a misspelling, a misquoted article, or a parody that uses the incorrect version. These artifacts are not proof of a changed timeline. They are proof of how common the confabulation is and how errors propagate through culture. The Mandela effect, therefore, stands at a fascinating crossroads. It is a real and deeply felt experience for millions, a genuine psychological phenomenon of shared false memory. Yet its most mystical explanations may simply be our modern attempt to mythologize a flaw in the human operating system, a bug in our memory software that the internet has learned how to mass produce. It forces a humble question: if we cannot trust our own recollections of a cartoon bear's name, what else in our past might be a story we have unconsciously written and then together convinced ourselves is true? Jean Ray's time cube stands as a stark monument at the outer fence of human speculation, a theory so divorced from conventional science that it becomes a perfect case study in how fringe ideas are born, spread, and endure. Its emergence wasn't from a laboratory or a peer-reviewed journal, but from the passionate, frustrated conviction of a single individual. Ray communicated his cubic vision through rambling, poetic online manifestos and homemade websites plastered with dense, capitalized text, a classic hallmark of fringe communication. This method bypasses the traditional gates of scientific scrutiny entirely, appealing directly to an audience that distrusts those very institutions. The presentation itself, often perceived as chaotic or cryptic, becomes part of the theory's identity, signaling to adherents that they are accessing forbidden or elite knowledge hidden from the mainstream. The persistence of such ideas, even in the face of total scientific rejection, reveals a deeper human dynamic. For some, the appeal lies in the sheer act of rebellion against a perceived monolithic and arrogant scientific establishment. The time cube wasn't just a theory about days, it was a weapon against what Ray called educated stupid, a rejection of all accepted authority. This taps into a powerful undercurrent of anti-intellectualism, where complexity is seen as obfuscation and simple, bold declarations feel more truthful than nuanced, evidence-based models. Furthermore, these theories often fulfill a deep psychological need for order in a confusing universe. The linear, one-day model feels mundane, but a cosmic cube with its simultaneous corners and hidden geometry makes the viewer feel like a pioneer, someone who has cracked a code everyone else is too blind to see. It transforms the follower from a passive consumer of knowledge into an enlightened insider, part of a small group that possesses a revolutionary truth. This creates a powerful community bond, insulated from criticism, because any rebuttal is simply seen as further proof of the mainstream's conspiracy to suppress the truth. The time cube and theories like it ultimately persist not because of their scientific merit, which is non-existent, but because they function as a form of philosophical or even artistic expression. They are cries against the limits of human understanding, shaped not by data, but by the raw desire for a universe that is more mystically structured than our equations suggest. They challenge us to ask, where does reasoned skepticism end and closed-minded dogma begin? And in their defiant, chaotic existence, they remind us that the human drive to explain reality is so potent, It will sometimes build castles in the air when the ground feels too solid, too ordinary, and too controlled. We have wandered through a labyrinth of 50 realities, each more bizarre than the last, from a universe that might be a simulation to a cosmos that could be a single, thinking mind. We have stretched the fabric of what we call real to its absolute limits. We have stood at the edge of black holes that might contain other universes, questioned whether our moon is a machine, and wondered if our own memories are proof of other timelines. Some of these ideas are grounded in serious mathematical inquiry, while others live on the wild frontiers of speculation, but every single one serves a vital purpose. They are not just stories, they are stress tests for our imagination, daring us to think beyond the textbook and question the very ground beneath our feet. They remind us that the universe is under no obligation to make sense to us, and that the most profound truths often lie hidden in the questions that seem the most absurd. Science advances not just by confirming what we know, but by daring to explore what we do not. So now we turn the question over to you. After this journey through cosmic chaos, which of these 50 theories shattered your reality the most? Was it the chilling silence of the dark forest, the intimate paradox of quantum immortality, or the ancient celestial drama of the Saturn death cult? Let us know in the comments below. Dive into the conversation with fellow cosmic explorers. If this voyage into the unknown stretched your mind, give this video a like to help others find these mysteries. And subscribe, because the universe is stranger than we can suppose, and together we have only just begun to map its endless, bewildering